lightning talks, and some networking. And we'll begin our day with our keynote, Dr. Emily Carl at 9:05. I just want to quickly reiterate a few tips for making the most of the online platform. If you are having any technical issues, you can put them in the Q&A, or if you have anything that can't be solved, please just email me at mercedes.randall@reans.co.nz, which you can see up on this screen here. I will be monitoring my emails throughout the session for any urgent inquiries, so please just refresh yourself as well for the code of conduct and housekeeping. There isn't too much else for me to say for now, so I'll hand over to Murray, who will take you through this morning's keynote session at 9:05. But just in the next couple of minutes, just relax, grab a cup of coffee, and we'll see you very shortly for our first keynote speaker of the day.
Okay, everyone. I'm pleased to introduce Dr. Emily Carl. Emily is a supercomputing applications specialist at the Pawsey Supercomputing Research Centre, where she works to improve computational chemistry and materials science capabilities at Cetonics. Her main areas of interest are in improving the uptake and usability of GPU-accelerated computing for applications in computational chemistry, especially for free and open source software. She has supported and written code for a wide range of applications in computational molecular science, with her code being used by research groups around Australia, New Zealand, and the world. So, over to you, Emily.
Thanks, Murray. So, I'm going to talk a little bit today about a bit of an unusual topic, but one that is, I think, very important to science, which is code archaeology, or less facetiously, legacy code. Because when Mercedes was asking me to give a keynote here, one of the things she mentioned was talk a little bit about your career. And my career has been weird because I spend most of my time working on code that is substantially older than me, and in some cases older than my parents. So let's get started. So first of all, about me. Actually, can everyone see my slides first? Just make sure that's all good. Awesome. Thumbs up. Excellent. Yeah, like Murray said, I'm a computational chemistry expert, so I use computer simulations to study chemical reactions from first principles. I work at the Pawsey Supercomputing Centre in Australia, working remotely from Brisbane, and my role is kind of a mix of research support, software engineering type stuff, where I help researchers make use of our supercomputer. So very briefly, Pawsey is Australia's national tier 1 supercomputing facility, or one of two rather, headquartered in Perth, but everyone working for it is pretty well spread out throughout the country. And we run the Cetonics supercomputer, which is Australia and indeed the Southern Hemisphere's largest research supercomputer. And it is also the fourth most energy efficient, which is pretty nice, and by far the largest system in Australia. And if you're wondering about the name, Cetonics brachyurus is the scientific name for the quokka, which is Western Australia's really famous and friendly little marsupial. So it's become kind of an unofficial mascot for us at the centre. And really, our job is to make science happen in Australia and really accelerate discovery like that. And a big part of that is making sure that codes that people use, that researchers need to do their work, are well supported on our cluster. And a large part of that is we have to meet researchers where they are, right? If people are using widespread code, then we've got to make sure that it works. Right, let's talk a little bit about the history of scientific computing. I swear I'm going somewhere with this. This isn't just a complete tangent. Scientific computing has a really long and storied tradition, right? Computation being part of science and research goes back as far as least as Leibniz, definitely Ada Lovelace in the 19th century. It long predates electronic computers that we have now. So there's this wonderful quote by Ada Lovelace where she's talking about the analytical engine, which didn't actually exist at the time. This was like Charles Babbage's project that he had this cool idea for a mechanical general purpose computer, but never got around to actually building it, which is very classic. I'm sure we can all relate to that kind of stuff for side projects. And she thought that the analytical engine, it weaves algebraic patterns just as the Jacquard loom weaves flowers and leaves. The cool part about this is she thought about using it for more than just crunching numbers, but really to think, to do science, to reason about how we would actually do kind of formal logic, right? And it got its modern form, scientific computing, that is. Even though Ada Lovelace never got to actually experience a lot of this stuff, she died tragically early. It really started to kick off properly in World War II during the Manhattan Project and with the Bletchley Park cryptography, so breaking Nazi code ciphers in Bletchley Park. So the thing about scientific computing is that it bridges the gap between pure theory and experiment in science, right? It provides new insights that can inform both. So technically, you can think of scientific computing as a branch of theory. I often do when I'm talking to people, but really simulations give us something that analytical, just writing down equations and solving them algebraically doesn't necessarily give us, right? Number crunching, data processing, visualization of stuff gives us a insight into how systems work, right? That is almost like a digital microscope. You can simulate all of the individual details. You can do some counterfactuals. You can play around with it and get a real, deep visualization at first principles as to how these complex systems are working, which is really cool. And this scientific computing, it's a tool, right? It's a really powerful tool, and it has to be in service of science. So getting back to the history. Early electronic computers were ludicrously primitive by today's standards, right? They were somewhere between room size for mainframes or fridge size for mini computers, which is a very funny name when you consider, they're the size of a fridge or a washing machine or that sort of thing. But you got to remember what they were, going up against later on. Um, they had tiny amounts of memory, tiny amounts of compute cycles, and really high latency input-output stuff. It was very, very primitive. Again, you had punch cards to put your input into the computer, so your code. And you had physical printers, so you didn't have screens. You just got an actual piece of paper with a printout of the results. Now, I love computer history. I don't know if we have any computer history nerds here in the chat. And it's kind of easy to be nostalgic for this stuff at a distance because it was a time when, there was all of this ferocious innovation going on in computing, right? Um, but these machines objectively suck to use. Like if you talk to old people who were around at the time, right? Which I have on many occasions, they will tell you that like the workflow process that you had for this, um, essentially when you had your source code, you put it into a deck of punched cards, these physical pieces of cardboard that I have on the right. And then inevitably you would drop your deck of cards because each card was one line of code, right? So you had a whole stack of them. And if you drop them, they're out of order, have to put them back into order and hope that you numbered the lines properly. It was a hugely frustrating process. So you give the punch cards to the wizards, usually women, sometimes cats, like in this picture, who operated the machine. And then you had to wait until your job finished. These were all batch processing things. There was no interactive computing at first. So your job would run when it run, and you had to hope that it ran correctly. If it didn't, you would get a piece of paper that would give you either wrong answers or you just get told by the computer operators, hey, this didn't work, it crashed, you had a syntax error, or, your code, had some numerical error in it. You had to try and debug it in this incredibly slow, frustrating feedback loop, right? So as a slight tangent, when I said that the computer operators used to mostly be women, this is extremely true. Computing used to be seen as women's work. And I mean this, unfortunately, society means this in the derogatory sense, right? Um, there's this wild quote by Grace Hopper, who is the creator of the first compiled programming language, COBOL, this huge titanic figure in the history of computing. And, she said, it's just like planning a dinner. You have to plan ahead and schedule everything so it's ready when you need it. Women are naturals at computer programming. So this is fascinating to me, right? This little advert on the right that I just found on the internet is like a view into this completely different mindset where they viewed like computing work as essentially secretarial stuff. It was low status, it was relatively mechanical, and it was seen as something that women were a natural fit for. And unfortunately, because of the way societies tend to work, that meant that it was devalued. Programming became popular and profitable with personal computers, and especially the dot-com bubble that started in the US and spread to the rest of the world. And suddenly, now that this was a profitable thing that you could do and something that was professionalized, the message shifted to, oh, girls can't program. It's a natural, like men's career, that sort of thing. Why do I bring this up? Well, I bring this up because exclusion based on gender in these fields is completely arbitrary. It's gone in cycles based on profitability and clout as a career, and this happens a lot. And we're in, thankfully, a cycle where things are shifting back towards, hey, it's good to have women in computing, women can do computing, shock horror, and that we are all better off when we include people in this field, which is fantastic. But, this stuff is basically arbitrary and based on social whims. And if you want to learn more, there's a fantastic book called Programmed Inequality: How Britain Discarded Women Technologists and Lost Its Edge in Computing by Ma Hicks. That's a tremendous history of essentially how this process played out in Britain and why it was bad for them. So getting back to the history lesson, Fortran was the OG language for scientific computing. This was the first high-level, i.e. not machine code, not assembly code, compiled language for scientific computing. It was aimed specifically, the name comes from formula translation. It was designed by IBM back in the 50s for punch cards, right? And so this really slow, agonizing process of getting code to actually run on these primitive machines with incredibly limited resources, that's what Fortran was designed to do. And a lot of these design decisions make sense in the light of that stuff, right? It had the first ever production optimizing compiler written by Frances Allen, another titanic figure in the history of computing, off to the right. And she made it so that you could write relatively portable and, if we're being generous, readable code and still get good performance. You didn't have to fine tune for the specifics of your machine, right? Fortran, like I said, has heaps of really weird quirks. It's a very strange language, right? And if you're coming to it from the perspective of someone who's, had the good fortune of learning via Python or Rust or something else like that, a nice modern language, it can be quite jarring to come across these very strange, archaic things from the past in computing. Bits of it have been fixed. There's a really impressive effort that started during the COVID pandemic to modernize the language and try and bring it forwards into the 21st century, but a lot of it still hasn't, and it's still quite idiosyncratic. And frankly, not very many people know how to use Fortran, right? Why am I talking about this? Because Fortran is still around. There's this attitude in science, right? Especially because, as we all know from being at a research software engineering conference, research software engineering as a profession is still in its infancy. It's kind of difficult to get, stable career paths doing research software outside of, for example, US nuclear weapon systems on the right, although even that's not quite stable anymore, right? But there's this attitude where, because it's so hard to get people in to sort of work on code as their primary job, if it ain't broke, don't fix it. Right? So there's heaps of critical infrastructure for scientific computing that when you dig down into the lower levels, into the hindbrain, or perhaps mitochondrial DNA is a better example for it, heaps of it is written in Fortran and still goes forwards in Fortran. Stuff like linear algebra libraries, physics, chemistry, engineering, differential equation solvers. There's a lot of this stuff that was written in Fortran decades ago and is being dragged along because it still works, right? It might not be the most robust, it might not be the most easy to use or easy to maintain, but it's there and it's battle tested and we know that it's correct, which is really important, right? But the thing is, someone has to maintain this code. It isn't just kind of going to magically keep going on, right? Like some artifact. Someone has to do this. And you can make a career out of doing this if you dare. Right, with the history lesson out of the way, let's go to a slightly different history lesson. Let's talk about the history of Scientific Emily. I'm going to talk a little bit about where I've come to, my position that I'm in now, and hopefully it'll have some useful lessons that you can all benefit from. In the meantime, I'm going to grab a quick drink of water while we take a break and make sure there's nothing super urgent in the chat. Seeing someone in the chat saying nightmare times with COBOL. That's extremely correct. COBOL's the other big one. That meme was originally COBOL, by the way, not Fortran. I had to modify it. Right, so here we go. My intro to program. I, like many people of my generation, learned to program by modding video games. I got started with a video game called The Elder Scrolls 3 Morrowind, and then I got into the emulation scene, the ROM hacking scene, making demos, that sort of stuff. I did my bachelor's degree at the University of Queensland in physics and computer science, and I did a summer research project in second year on atomic physics. Photon-atom interactions. So you have some atom and it interacts with light. And as we know from quantum physics, light is quantized. The energy of a particular photon is proportional to its frequency. And similarly, atoms, the energy levels are quantized. So an atom can only absorb specific characteristic frequencies of energy and emit characteristic frequencies of energy, or light in this case. And so you can see in the example down the bottom, when you shine your light through a prism or a diffraction grating to split it up, if you shine sunlight through a prism, you get a rainbow. But Joseph Fraunhofer, a German scientist, discovered, in the 18th century, that if you shine sunlight through a prism, you get these black bands appearing, these gaps where there's no light. And that gap corresponds to these characteristic frequencies of the atoms that make up the atmosphere of the sun. And he was able from that to deduce what the sun is made of, right? This is like a fingerprint for atoms. And calculating any of this stuff is really difficult. You can solve the hydrogen atom using a pencil and paper analytically, but everything else, almost all non-trivial research in atomic physics, needs some kind of computation. So I knew how to do a little bit of Python from my computational science stuff, but not how to do anything useful, right? So I had to really quickly learn that coding for research is very different for coding for hobbies or university stuff, or later on, I would learn for corpo work, right? Writing research code, it has to have a specific goal in mind, and often you don't know how you're going to get there, and you don't even know if it's possible, right? So there we go. After that, I went on to do honors with the same research supervisor, a guy named Michael Bromley, and I attempted to put the photon helium scattering problem on rigorous footing. So we can see on the right here that we have this example of a helium atom, and it's got some, photon comes in, it scatters off an electron, and then one of a few things can happen. Either the photon can go back out with the same energy that it came in with, so the same frequency, but it might just be deflected at a different angle. It could also donate some of its energy to the atom, so it comes out with actually a lower energy, so it's redder than it was when it came in, and again deflected at some angle. This is inelastic or Raman scattering. Or if it's a high enough energy, it can hit the photon, it can hit the electron, and just completely get absorbed and eject that electron out of the atom and ionize it, this photoionization process, right? So this mix of absorption versus scattering, this was a really old problem that people had attempted to sort of put on rigorous footing for ages, right? For literally decades. And my honors thesis project was to try and actually make sense of this huge zoo of processes and come up with an efficient way to calculate all of these. So I started by using and extending Bromley's atomic structure code, which was written in super old school Fortran from, back in the day when we had really early primitive computers, plus my own de novo numerical analysis code. Now, the interesting thing I learned through doing all of the research analysis and literature reviews was that this problem had been attempted in ye old days, in the 60s. And the scientists back then had to come up with all sorts of really interesting and really clever numerical approximations for helium and other atoms because they had such incredibly limited computational resources. They couldn't just spin up a 1,000-node system on a cluster. They had to be really strategic with what they did. And a lot of these old techniques had been forgotten. They'd been, passed on because we had much faster computers now. We had this, Moore's law increase in computer power from the 60s through till, quite recently. And so people just kind of went on and did the simple things and let the fast computers take care of it. But these approaches still worked, right? The fundamental physics, the fundamental science hadn't changed. So this stuff was really fast. When you take it and put it on a modern computer, it's like putting nitrous in the energy of a car, in the engine of a car, right? It means that you can do a lot more stuff than you would otherwise, or rather, you can do more science. Because to be clear about it, the best way to speed up your code is to do less stuff, right? To literally do less work. You can do all these clever optimization stuff or move to, different programming languages, but the best way is like if you can do less mathematics, less data processing or whatever, then you will be faster, right? And these old scientists were masters of doing this. And if you dig into it, there's a lot of wisdom there. So the lesson that I learned, the hard way during this honors thing was don't discount old stuff just because it's old. A lot of this stuff still works and still has value to it. Another lesson that I learned, I had a brief obsession with functional programming in my honors. Has anyone here used OCaml or any other functional languages? Um, I really like OCaml and I like functional programming languages. I played around with Haskell. I played around with Lisp, which is one of the really old school programming languages as well. Um, and as a result, I ended up writing chunks of my analysis pipeline in OCaml because I thought it was really fun, right? And it is. Lisp rocked my PhD. Hell yeah, Brent. So, previous. So yeah, I wrote a lot of my analysis pipeline in functional languages, and I basically had zero users use my code since then because no one uses OCaml in physics. Hardly anyone uses OCaml outside of a few finance firms, right? So unfortunately, it was not the right tool for the job in terms of getting it used. So lesson there, don't chase after new shiny stuff just because it's shiny and new. Um, Lesson 2.5. Some of you may or may not have the same brain as me. And if you do, you will know this problem, which is you'll hyperfixate on random cool things in computing or other stuff, right? And this is really dangerous. So have some hobby codes to soak up those inevitable hyperfixations and don't put it in production code. I learned that the hard way. So hopefully you can pick that up soon as well. My PhD. This was when we got the really good stuff. I went down to University of New South Wales in Sydney for my PhD with Julian Berengut. Started out really physicsy, again doing these atomic structure calculations, but realized that our group's physics code, Ambit, couldn't do what I wanted. So I decided to add the functionality myself. The options were either do different science problems or write the code. So I decided to write the code. I completely overhauled the parallelism model, changed and added new features in maths. One of the things that's, the most fun is off to the right. We have this little thing called EMU-CI because we did some clever approximations with the structure of the matrix that we have to solve the eigenvalues for as a big step in this program. And it looks like an emu's foot. So it's pretty cool. And it runs fast. So really cool stuff about this, right? Ambit is written in modern C++, and this really supercharged development. So some of these language features in C++, like smart pointers that make resource management and memory management not quite automatic, but it certainly makes it a lot easier than doing old school C, malloc, and free type stuff, as well as templates and other nice interface polymorphism, a little bit nowadays with concepts and that sort of stuff. Maybe that'll come through eventually. Who knows? But there's also stuff like there's tons of mature libraries out there from private companies like Google to do fast hash table queries or fast matrix maths that are written for C++ because C++ has a huge adoption in the private sector. All of this stuff supercharged development of the code. It made it a lot easier to develop this between the two of us and add new features and modularize it. And sometimes new stuff really is better, right? Software engineering is a really important discipline and it is separate to just writing code. And a lot of the stuff that we've developed in software engineering as a craft, as well as algorithms design, data structures design from computer science, those are really good. And we can benefit from that a lot in scientific computing, from learning what our colleagues in the private sector are doing. We open sourced this code in 2019, and it's now used all over the world. We basically published a paper in Computer Physics Communications talking about the numerical techniques that we used and the method for parallelism. And then we released the code under the GNU GPL license on GitHub. And this was a really great approach to getting tons of citations because people grab the code and then we say, hey, by the way, once you're using this, cite our paper when you do that. And this is now my most highly cited paper by a large margin. I've got, I'm still reaping the dividends from putting in the effort to open source this. And not just that, make it nice for people to use. You see, I mentioned up the top, I've got a nicer command line interface for Ambit. Just the fact that you can grab it and go makes it way more attractive than even atomic physics codes that might technically be faster on some architectures because they've got all this tightly optimized, assembly in it. But, if code is easy to use, people will use it. So publishing code that fills a pressing need can be incredibly good for your career. After that, I moved into research software engineering. I got a job at a computational chemistry group at UQ, group of Deborah Bernhardt. This was a different field to what I had studied in. It was chemistry rather than physics. But I got hired because I was adaptable and because I wanted this specific job. I wasn't settling for, research software engineering because I couldn't get an academic career. I wanted to be a research software engineer. And a big chunk of the interview for this job was sight reading Fortran. And this was foreshadowing. I had to pick up the basics very quickly and become an expert in a second field of science, molecular dynamics. And our group had really good MD code, but a lot of it was written in ancient Fortran. It was really hard for new students to use. And in fact, if you look at a lot of the open source, public codes, and even some of the really common proprietary codes out there in this field, they're all written in old Fortran, right? Because this stuff works. So in order to make it more usable for new students who oftentimes hadn't even seen a command line before, let alone, Fortran 77 code, I wrote a nice graphical front end in Python using the F2Py bindings and the Qt graphical user interface library. This turned out to be an incredibly good teaching tool, and we used it to onboard so many new students to the group. You can see a little example on the right of what it let us do. We have a simulation of how these particles are moving in a box. This is a liquid. It's called Leonard-Jones fluid, so you can think of it like liquid argon, basically. And what we could do is we could use the Python GUI to get live readouts on the state of the system by querying this Fortran code through these bindings. We could plot the results in real time. Students can visualize what the liquid is doing. And then there were some sliders off to the right so they could change things like the, pressure, temperature, size of the box that the fluid's in, that sort of stuff, and actually see how the system changes in real time. This was incredibly useful for visualizing how this stuff actually works under the hood. And being able to take a nice modern language with good support for graphical user interfaces like Python and then use that as a wrapper around Fortran was incredibly powerful. And this was around the time that we started to see this Fortran renaissance kicking off. And F2Py is quite an old tool, but there were a bunch of new stuff coming out that made this a lot easier. And the Fortran tooling ecosystem is surprisingly good, right? Wrapping Fortran in a modern e-interface now is nice. It's easy. And it's actually really useful. You can take this old code that would otherwise be sort of like people deliberately avoided using it just because it was so, it takes time to grok how Fortran works and to load it into your brain, right? So instead, by putting it in a nice friendly wrapper, it's almost like, taking a pill for your cat and putting it in a piece of cheese. You can get people using it, and then once they're familiar with the nice friendly interface, they can start modifying the Fortran code, and they've already got some exposure to it. And this, I think, is one of the things that can really help us in this field as research software engineering, this approach. During this time, I also did a little bit of private consulting. I took on some freelance work to modernize old Fortran code. So as an example of what I did, I modernized some old physics code that had been inherited from an old academic, or rather the client had inherited from an old academic. That was a mix of Fortran 77 and DEC Fortran. So this is something from the past, right? This is Tales from the Crypt type stuff. DEC Fortran has not been around for a very long time. DEC went out of business the year that I was born. So we're dealing with some really ancient code. It was fixed form, so you had a fixed number of characters per line. The column in which you print a character is actually meaningful, so white space is significant. This is all stuff that's inherited from the punch card era. Everything is super duper terse because again, this was originally for punch cards and then turned into a group of .f text files. So you had to be really economical with characters. This makes sense in context, but it makes it really hard to maintain. It also made it really hard to compile with modern tool chains, right? Because stuff has moved on since then. Computers have moved on since then. The Intel Fortran compiler was the only one that would actually agree to compile this code. And that's because Intel put a lot of effort into maintaining backwards compatibility for this stuff. And you'll find this a lot with old Fortran code. There were no comments in this. God, no, we didn't have comments. You wouldn't waste an entire card for just something that wouldn't be executed as code. And indeed, many of the variable names were actually transliterated from Russian. This had been, inherited by a Russian academic, transliterated from Cyrillic to the Latin alphabet, but hadn't actually translated it to English. So this was essentially a reverse engineering job, right? You might as well have given me an uninstrumented binary. There was zero chance of making sense of this by reading the source code. So skills from game modding actually came in really handy here. The kind of stuff where you're actually running through some, completely opaque binary. Well, this was effectively that, but it was, opaque Fortran, and trying to just like slowly build up this understanding at a really low level as to what this stuff is doing turned out to be really useful, right? Made heavy use of static and runtime code analysis to make sense of it all. Oftentimes, the only way to find what it was doing was to run the code under like a debugger or under, some Linux observability tools, like for example, BPF, which is a fantastic tool that is now in the Linux kernel and extremely widespread, to actually see what are you doing? Like, what files are you opening? What are you writing to here? Who is actually doing this? Um, the verdict was it was essentially impossible to modify or debug, given all of this stuff. There was zero chance that anyone other than the original academic could make sense of this thing, at least not without a tremendous amount of effort and learning Russian. So what I ended up doing was reverse engineering the bespoke input-output format that this had, which was a binary format, essentially, write a wrapper layer around it. Again, wrapping old code in some nice interface. Surprisingly useful tool when that's all you've got, right? And then essentially said, okay, we treat this like a black box library. Don't touch it. The thing is, it probably would have been better to rewrite this code from scratch. Spent a lot of time trying to dig into this, and the client was very insistent that like, no, 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 we don't want to rewrite it. This stuff works. We want to just do it. And I kind of had a bit of a gut feeling early on that this wasn't going to work. And perhaps I should have been a little bit more forthright about that. But at the end of the day, it would have been better to rewrite it from scratch and reuse the old code as a reference spec. Just essentially say, right, this is the output that this has. We treat it as a black box Oracle. We write code that reproduces exactly that output, and away we go. But that's life. They now have this nice library or at least interface to this library that they can use. And so, the lesson that I really took out of this was that, there is money in modifying and maintaining legacy code. Might not be easy to make a stable career out of this because a lot of it is in small research groups who have funding in dribs and drabs. But there is a demand for this out there, and there is people who are really screaming out for people who can actually make sense of this old ancient code. But you got to know when to cut your losses, right? If you've got old Fortran code, it can be understood, but is it worth actually taking that time to understand it? That's a real question of cost-benefit analysis, and it's going to depend on the kind of code that you're working with. So lastly, talking about PAWSI, I joined the PAWSI Supercomputing Center in 2024 as a research software engineer. Again, like I said, doing a mix of training and software development, as well as user support, so like tickets and that sort of stuff. And I make code go fast on Sotonix. So as I'm sure I don't need to share with people here because we're all research software engineers, combining software engineering with domain knowledge is really powerful. The number of times there has been a problem at my work where I have had to try and fix some gnarly bug in a computational chemistry code, and actually it turns out it's something where they've done some weird numerical routine that isn't actually physically well justified, right? So this is the kind of thing where being an expert in molecular dynamics or computational physics and also software engineering is a really powerful skill set. I mostly work with these computational chemistry codes now, and again, the ones that are commonly used by the research community. Both old and new. Like I said, I have some code that I'm working on right now that is actually a lot older than I am, and just trying to get that working and fast and running efficiently on Sotonix is quite challenging. Again, getting it to compile at all is difficult, right? But at the end of the day, supercomputers and all of this nice hardware is no good if you don't have code to run on them. The point is to do science. The point is not to make a computer that goes fast. The point is not to make a nice, elegant software artifact, even though that's really satisfying when you can do it, right? The point is to do science, and it has to serve a scientific need. And so really, you have to meet researchers where they are. And where they are is often, this is a tool that works. This is a tool that gets science done. I want to keep using this tool. That is understandable. They don't get paid to write code. They get paid to do science, right? So that's the real lesson that I've learned from being in a sort of software-focused, client-focused environment. So yeah, summing up, legacy code is everywhere in scientific computing. There's potential huge gains from using it effectively, both optimizing it to make it run fast, although frequently it already runs fast, right? Like I said, it's meant for resource-constrained environments. You put it on a modern supercomputer, takes off like a rocket. But also things like making it more useful, right? Making it easier to use, giving it a nice interface, wrapping it in some modern code language. Modern tools are really useful. Don't discount modern tools, right? Obviously. But when you combine them with the old ways, you can get some really, really great scientific results out there. Things like graphical user interfaces, really handy for actually visualizing data and understanding a system at play, and also making it easy to use. Again, static and dynamic code analysis, really, really powerful tools. There's a lot of great tools out there for static code analysis and formal verification that are, I think, being slept on and are really worth checking out. And reverse engineering tools, again, it's really great that there has been this huge renaissance in reverse engineering out of the retro computing space, out of hobbyists, essentially. And us in the professional field can use that stuff. Knowing some computer science is a superpower in scientific computing, by the way, as well. Many people have come into this field and they know just enough to get by and no more. So if you have a little bit of a rudimentary understanding of algorithms, data structures, formal verification methods, user interface design, code optimization, that sort of stuff, you can really stand out from the crowd. And there's huge gains to be made by applying some of this knowledge from academic computer science in the private sector to scientific code. Being a computer history nerd is actually useful. Maybe I'm a little biased in this, but the number of times that I've come across some old piece of legacy code that I've had to maintain and go, hang on, I recognize this, dig around in my collection of old computer manuals and find the manual for the system it was written for, that then lets me make sense of it. That's actually really handy, right? And the Internet Archive is your friend here. There's tons of old stuff out there that you can look at. And then lastly, legacy code isn't going anywhere. It can be a career if you can stand the psychic damage from it. And with that, I'll say thank you and open up to Q&A.
Cool. Thank you very much, Emily. Very engaging. Well, people can throw their comments in. Oh, we got one from Alex already. Would you now be able to use AI to find out what code does, going back on your experience as a legacy code consultant?
No, at least not in current thing. So AI, the way it works, modern large language models are statistical models trained off large amounts of data. If you have trained the code, or if you're using software that is within a section that is well covered by its training data, like for example, Python or C or that sort of stuff, then it can maybe give you decent results. If you're using old Fortran, there's not a lot of old Fortran in the training data sets for ChatGPT or any of these other large language models. So my experience is that it really struggles with old Fortran. You give it some Fortran 77 and it just has no idea what to do with it. What I think is perhaps more useful than AI to find out what code does is these formal analysis and static analysis tools, ones that hook into your compiler toolchain stuff and are actually using the ground truth of your code being translated from, in the compilation process, you take your source code files, they get, lexed and parsed, turned into an abstract syntax tree, then intermediate representation run over by the compiler, spits out optimized machine code at the end. Stuff that operates on that abstract syntax tree level is incredibly powerful, especially if it preserves the mapping back to the source code. So that stuff, because it's operating on the actual ground truth of what the computer sees when it is compiling the code, that is the really powerful stuff out there. And there's open source static analysis tools out there, a lot of them actually built into the Clang and LLVM programming language. So, check out essentially LLVM's code analysis tools. That would be my advice rather than LLMs, because I think you'll come a cropper if you try to use them on Deck Fortran.
Cool, thank you. Shane asks, I've observed a lot of old ideas resurfacing as new ideas because of lack of historical knowledge. Do you think training should include a more history of computing?
Oh, that's a fantastic question, Shane. I think it would be really useful to have some history of computing knowledge out there. Um, you could definitely see it as keeping it field specific. So, if you're learning computational physics, learning some of the old comp phys stuff. If you're learning compiler theory, learning some of the old compiler theory type stuff. But yeah, no, this is true. A lot of these problems, I'll see stuff where people will come up with some idea in a new programming language and go, hang on a minute, that's just a Lisp. But like Lisp did that back in the 70s. So yeah, no, I think that's a fantastic idea. And if anyone here is doing training for computing stuff, uh, yeah, keep that in mind and hit me up. I'd love to chat about it.
Ellen asks, Do you find legacy codes more optimized due to the limitation of computation power? There is so much in the open that is poorly optimized now, probably also a result of programming being more common.
Yeah, I think you really hit it on the head with the second point there, Alan, as a result of programming being more common, right? Like I think, there is a lot of stuff where, yeah, these legacy codes, because they've been, especially ones that have been continuously maintained for decades, these are really well optimized for often single-threaded environments, but you can make work with that. But yeah, I think it's just a fact that there's a lot more code out there, so there's going to be a lot more dreck. Like there was probably also really bad code back then. It just hasn't survived. There's like selection biases there as well. But yeah, I think due to the limitation of compute power, they were tightly optimized numerical routines. And this is why, for example, LAPACK under the hood, which is a linear algebra thing, if you grab the default implementation of LAPACK, it's Fortran code and it's still really, really fast because they've like optimized every single little operation that they can have on it.
Matthew asks, do you think there are differences between how scientific programmers work compared with commercial developers? I'm thinking the approaches like test-driven development, do they have a place in ensuring that codes are correctly doing what they claim to? And what about agile? There's a follow-on, also interested in the thoughts about cultivating programming skills in non-RSEs.
Yeah, that's a really good point. Um, To talk about cultivating programming skills in non-RSEs, I think it's definitely doable. I think the thing that I've had the most success with is in showing have when people have a goal that they want to achieve and the current software doesn't have the capabilities to do it. And that's when you can really swoop in and say, hey, by the way, if you learn just like a little bit of Python, you can make this work yourself and you don't have to wait on one of us to actually do that. And I think that's an area where like having these, curated beginner resources that people can do on their own, like the carpentries, and making it widely available and widely known, and then letting people come to it in their own time would be my sort of approach to that. And then if people feel like there's a need that they're fulfilling by learning to program, then they'll do that. That's certainly how I learned, right? Way back when I was a teenager. As for like how scientific programmers work compared with commercial developers, definitely. So test-driven development is a really good one there, a really good example. I have found that like many of these codes, especially legacy codes that claim to work correctly, they don't have any testing at all, right? And the first thing that I do when I come into one of these projects where I'm like looking at, some piece of old software is if it doesn't have tests, sit down with the researcher and basically say, right, come up with a test case for me that is like, this works. And then we'll write a set of automated tests that treat that as a specification. Even if it's just an end-to-end a smoke test, which if you're not familiar, smoke test is you're testing a printed circuit board or some electronics, you plug it into the wall outlet and turn it on, and if smoke comes out, then it's busted. So literally run the code and see if it crashes type tests, but having it be automated. There's none of that, or very little of that, except in really big scientific codes, which I think have learned it the hard way. So a lot of these public codes have learned the hard way that test-driven development is a good idea. Continuous integration is a good idea. The private sector sort of figured this stuff out, and it's taken a long time for it to bubble into scientific programming. So yeah, I think that's one of the biggest ones in this field. And I think we really should be focusing more on that. As to Agile, I don't know. I can't really speak to Agile. I've never worked in an Agile shop. Um, Everything I've worked in has always been a very ad hoc environment. So yeah, make of that what you will as well as a management pattern or anti-pattern.
Right, Brent asks, do you have any views or observations on the relationship between language density and resulting quality? For example, C++, C Sharp, Java, etc. are lower density, so easier to unpick, but more code to write versus Lisp versus languages like Prolog at the extreme end, but undeniably cool.
Yeah, no, I mean, they are very cool. And certainly if you try to read Lisp code or old Perl code or something, it's basically unmaintainable. I think language density is a really interesting point that I hadn't actually considered as to like programmability and readability. It often just gets called readability, and I would say like something like Python is even more focusing on having a low density, like being very heavily dependent on white space for formatting. Yeah, I would be inclined to agree that I think code being more readable tends to make for better code, just because it's easier to maintain and bugs are likely to stand out more often, especially to novice programmers. An expert Fortran programmer or Lisp programmer probably has learned enough that they can look at some terse old Fortran code and just immediately spot the issue. But that's not me, and I don't think there's anyone under the age of like 60 who can do that. So having it be more readable is probably more likely to get bugs fixed, so probably more likely to be higher quality.
Shane throws in alternate question, top-down or bottom-up programming?
I'm somewhat ashamed to say I don't actually know what that means, Shane. Can you elaborate, please?
Just to prove I'm a real person. Yeah, so back in the day when we started doing procedural programming,
Hmm.
two approaches. You could do top down. Basically, you write your code as a bunch of functional blocks that you're going to fill in. So you write the sort of major structure of the code, and then you fill in all of the individual subroutines and build it out
Hmm.
like that. Or you would start with all the individual little subroutines at the bottom and sort of build them back up into a full program. So the latter was probably more like you would do writing in Forth, whereas top down, I guess, yeah, a structured language, something like I guess C, you could do it that
Mm.
way. I tend to do both, to be honest. I sort of do the sort of top down overall architecture, and then I fill in from the bottom and work my way back up. But the bottom part is you can do testable individual routines. And then you gradually build those up. But of course, it's also a way of building libraries because, I mean, bottom-up programming is essentially
Mm.
programming with libraries.
Yep. Yeah, no, that was going to be what I was going to say. When I write something that's going to be a utility library, I'll do a bottom-up type approach because often I will have an idea for like, oh, if I do this little numerical kernel and then wrap that around it, that could be quite useful. Um, yeah, I don't know. I'm gonna say, give an ultimate question, ultimate answer, top down. There we go. No nuance, top down only.
Fair enough. I disagree.
Excellent. No, the real answer is it depends, as we've already said, but that's boring. That's the answer to every question.
Yeah, I think it also depends very much on the language you're working with.
Mm,
And I mean, the other question about the sort of density of a language is interesting. I hadn't thought about it myself because I'm a very old C programmer and quite a lot of hand assembly as well because compiler optimizers work. But sometimes you can't be knowing exactly what the code is doing and getting right deep in
mm,
there. But yeah, the languages. There was an interesting survey years and years ago, I think it was, about the number of bugs and whether something like Java produced less buggy code than something like C. And in the end, the observation was that it wasn't the language that improved the bugginess. It was the programmers themselves, the technology that they were using wasn't relevant. It was how good the programmers themselves were and how much care you put into it. So you can write very, very bug-free code in something like C, and you can write buggy code in something like Python or Java or whatever. It doesn't seem to matter.
Yeah, what I would push back on a little bit though is that yes, you can write bug-free, correct code in C, but the language won't help you with it.
Oh,
And in fact, you often end up having to fight back against it, right? So
mhm.
it is still a tax on developer productivity. I still
Sure. Yeah,
think,
yeah.
yeah, language does matter to some degree. Certainly, I found myself, much more productive writing in Rust, for example, just because it has all of these nice interface contracts and you can outsource some of the work that way.
Yeah. The other interesting thing, particularly when we're looking at parallel processing and high performance compute, is the amount of effort that's gone into trying to get implied parallelism from sequential code. This was particularly
Hmm.
for old Fortran programs, and with the introduction of things like Fortran 90, where they were trying to get that sort of implicit parallelism into the code to get it to perform well on machines like Crays and such. versus just tossing it and writing it again. As I mentioned higher up, my professor of parallel processing back in 1990 talked about the dusty decks, because even then we were dealing with Fortran code that was written in the 60s and nobody wanted to rewrite it. But the amount of time you spend trying to get this old code to perform on a high performance computer, you've got to think, well, is it worth it, or should I just rewrite it from scratch in a language that is actually parallel, such as Ada or Arkham was what I started on, or C Star, which was the language we used on the connection machine. And that's always the problem when you're looking at programming and dealing with some of these supercomputers, is to actually get the best out of them. I mean, Cray made huge amounts of money by making machines that could run old Fortran code very fast without any modification.
Cray's Fortran compiler is still really good.
Yep.
We have a Cray system at Pawsey, so yeah, that's very much on my mind. Yeah, and you make a good point about the parallelism stuff, and often that is the sticking point with a lot of this old code, was it wasn't written for massively parallel workflows. And if you're getting, back to say the 90s when we had MPI for message passing on nodes, that stuff mostly works okay-ish. Like it's still, you can compile it, it's still got some understanding of distributed parallelism. You might have to make some changes here and there. But like, yeah, any further than that and really getting it to work multi-threaded is a struggle. And I kind of just have it as like, pick my battles. Like, okay, I know the single-threaded performance is probably going to be good. So let's just like find the hotspot, put like an OpenMP loop around that or whatever, and then just let that run in parallel and say that's going to give us some improvement that's good enough. And then
I've got a
just,
question.
yes.
If you had to pick a person in computational history, who would be your favorite? You had a couple in your
Oh,
presentation.
oh, that's a really good question. I reckon, give me a sec. Archimedes. Archimedes, way back in ye old days, was coming up with these numerical computational techniques and using them as essentially intuition pumps for mathematics. So he would do some numerical, what we would recognize now as numerical integration, to come up with an answer for the volume of a cone with the same sort of, base area as the perimeter of a circle or whatever, some complex geometric thing. And he would do these really complicated numerical analysis stuff by hand and then work backwards from that to go, well, this is what the formal proof must actually look like. And in the process, basically came really, really close to inventing calculus 2000 years ahead of schedule. And this is a guy who was like, if he just made that little extra leap, towards infinitesimals and infinities, maybe we would have invented calculus 2000 years ahead of time. But certainly when you read a lot of Archimedes proofs, they read as like shockingly modern and shockingly readable. So there you go, a bit of a left field answer.
Definitely was not expecting that. Do we have any other questions coming up, or have we managed to? Great presentations.
Yeah.
I think we may
No,
have.
thank you for
Thank you very
for all of
much.
the great questions, everyone. This has been fantastic. I'll go back through the chat messages as well because I can see there are some bangers in there. I have a bit of a read.
Cool. Thank you very much, Emily. And I'm sure everybody can do their virtual applause.
Thanks for
Cool.
having me.
Yeah, thank you very much. Our next session, or our next speakers, isn't scheduled till, I'll check my handy dandy program. I believe we've got 10:05 down, which means that we have 10 minutes to have a quick break, refresh yourselves, and we'll kick back off at 10:05. Lauren, if you're there, if you want to get your screen shared, we'll be able to start in a minute.
work. Do you
Cool.
see that?
Yep. All right. Welcome back. Hope you had a brief break. So we're going to have two talks in this next session. First one is Shaping the Future of Scientific Software with AI by Florian. He's a research and development data scientist and seismologist who bridges geophysics with cutting-edge machine learning, develops real-time operational systems for geohazard monitoring, combining deep technical expertise with a focus on clarity, impact, and collaboration. Over to you, Florian.
Thanks, Murray. And very pleased to be part of the conference. Yeah, I was really impressed by the different talks from yesterday and this morning as well. Very interesting stuff. So first, I wanted to, if I can change my slide. Okay. Just to introduce a bit of what we do and a bit of my team. So it's also nice to see so many others from ESNZ, I guess more from the newer business units, but very exciting times, I think, for following the merger between GNS and NIWA. So we are from the GNS business unit, we are the AI and advanced analytics team. And briefly summarizing a few points what we do. We thrive in data science and machine learning pipelines. So you've probably seen Christoph Müller's Rambo talk yesterday. Or if you didn't, yeah, I recommend to watch it. But we also, everything we do goes through containers. So basically applications running in their dedicated environment, a bit like a virtual machine, but you can have multiple ones for specific tasks. And also, of course, we are very dedicated to operational and support of geohazard monitoring, especially the National Geohazard Monitoring Center. And I also encourage you to attend Jen Andrews' talk at 11:25 that will introduce a bit of well, basically what we do and what we support. And like it was told yesterday, code is cheap, and yeah, it became quite common in our team to use AI to code, so it makes us obviously faster. But today, yeah, I'm here to talk about what we do in terms of generative AI, and we do all sorts of applications, and some I selected a few of them. But first, yeah, I just wanted to introduce a bit of what we experimented with RAGs. And so RAGs are retrieval augmented generation. So it's basically plugging your LLM to some kind of knowledge base or documents, database, all sort of documents, and create that LLM that will use that database for context clues. So we actually started doing this with a news article about weather events. So that was part of Hadley Tidy's internship in 2024. We investigated climate disclosure reports, and we tried different models at the time to see how well it compared to an actual human retrieving that information in this 100 pages PDF documents. So quite encouraging result at the time. Probably could be better now with more recent models. But also internal planning documents. So exploring the database, notably the library Postgres database that we have here. And so, for example, Rob, who's working with me on this, created that library chatbot where we're trying to make it work. And as you can see, depending if you say, if you call the author Rob Buxton, Buxton R, or R Buxton, you get different results. So we kind of trying to figure out how to make it work the best. But yeah, about current developments, the last thing we actually did was about monthly reporting, so nothing about science. But we kind of figured that this is one of the tasks that was a bit the least engaging in our team, because we never really know what to write or why we should write this. So basically, sometimes we miss the impact of our work. It would be inconsistent compared to other teams, and like in the details or even the quantity. So yeah, we figured like we probably should be using AI for that. And how to make it more engaging, where basically we are using a Trello board to drop all sorts of updates. You know, I figured that out, I coded that thing, I made that dashboard. But the idea is that there will be some kind of AI, so I hope you can see my mouse, in a container running on Guest, which is the platform we have internally here. So we have this container working with a Trello worker, RAG, and another LLM that format outputs into the monthly report format. So basically, that Trello worker will actually pull the updates and link them to an internal documentation. So it could be the internal roadmap, it could be some goals or things like this, to actually grasp better where our updates can have an impact, for example. So yeah, it makes it more engaging. It's easier for us and our team leader that just have to pull the monthly report on the 1st of September. And yeah, you can play around with the prompt. You can make your report more jolly or more serious, as you want. So yeah, just a bit of couple of words about Guess. It's basically a platform where we can deploy containers, and we have that running through the GitLab CI/CD. So we can build the containers, the image, sorry, and deploy them on that platform. So we have all sorts of applications running, mostly for monitoring and operational stuff. You will see that with Jen's talk. Yeah. But yeah, a bit more serious and more sciencey. So you might know, some of you, about Rescape. So that was developed between NUA and GNS, so basically ASNZ now, and some others. But what is Rescape? It's basically a software for multi-hazard risk analysis. So you can, for example, if you want to know what's the impact of a flood or a tsunami on a set of building or a city or something like this, you can do that. But you could also add other hazards like landslides and some other things. And you can go really deep in terms of the details of the output of the model. So the number of people impacted, if you have that data. So it's very powerful. But the main problem, because I kind of relate because I'm learning how to use it, the learning curve is really steep. And talking with the developers and the project owner and etc., they told me that basically led to some of the users to actually just ask the team to do the stuff, the analysis for them, and then they will just use the result. So that made us think that maybe there is a way to make it more engaging for the user, especially the new ones that don't have any knowledge about Rescape and how it works, and all the basically the pipelines and the plumbing system. So we thought about making an AI agent that would be replacing basically the interface between the user and Rescape, the Rescape engine, which works with CLI command. So we talk about, people talk about this yesterday, but basically the difference between an AI agent and just a regular LLM is basically having tools. So it can fetch data, run code, it can act. It has memory, of course, but LLMs can have that as well. But most importantly, it has some kind of reasoning loop. So it can, when you query something, let's say, I want to analyze this tsunami inundation map with respect to Wellington, then it has to, or it will understand that it needs to pull the tsunami inundation data sets and look for the data that correspond to the building layout of Wellington, for example, or the population density map, something like this. So this was this first prototype of the Rescape AI assistant, which is actually more an agent, because assistant, I think we understand that more maybe in terms of documentation, providing help to the user, but here it's really you ask the agent to do something for you. So it can upload your data, run risk analysis pipeline. So it's a preliminary prototype, but it's a prototype, but already quite powerful, and we think that we could do much more with it in the future. And it's in my title, but so there are agents and agentic workflows. So basically giving the capability of reasoning to your agent. And so as basically a hands-on test, because we are basically learning anything about generative AI with the students that worked with us over the summer, or hands-on experiments. So basically that was one of my first experience with agentic workflow. And at GeoNet, so in the GeoNet program in ESNZ, we collect a lot of data. That data will be used then by external users, or actually to monitor some geohazards in New Zealand. But there is a lot of data, as you can see, different domains. There's many stations, tons of records. And they already did a great job, like a great web page for you to explore. But I was wondering if we could have a more like a human interaction about this. And so I kind of pull a random location in the database and look for some data. So my question to the agent was, what was the median lake temperature at the Waimangu Inferno Crater Lake in the last 2 days? So that's technically, if I were to do that myself, I would pull at least a couple of query to that tilde API of GeoNet. So yeah, I would actually start by wondering where this is, because I literally took it randomly. So I would look at the tilde API Explorer and look for the closest sensor. Because not quite that's nothing here, but yeah. So yeah, it would take me a bit of time, but what would the agent do basically? It would actually start to think about what tool to use. So it would query what the API that's called the data summary, or the endpoint, if you want, of the tilde API. That kind of give you a lot of information about the sensors and all that stuff. So when I ask this question, it can actually infer that the station OT001 is actually located at this particular place. So that's basically a thinking, an action. So it's called the data summary. It gives an action input. So in this case, I'm asking the agent to give a URL, so it can query that URL. And then it will actually think, it will observe and think, okay, did it get a satisfying answer? If yes, what to do next? So now that it knows the station, it's easier for it to actually look for the data directly, querying tilde. So yeah, it's gonna look for the data, download the table for the last 2 days. And yeah, I have another tool that basically briefly described that time series. And that's, so this is very directive. I mean, the tools are very directive and the questions are made to use the tools, but in the end, it's able, after 2 actions and a bit of thinking, to answer my question much faster than I would have. So this is very preliminary, but I think there is a lot of things we could do, especially to engage with the public in terms of what the data is being created. Writing the tool was actually pretty easy. So, you know, it's like using request package in Python and return the JSON. Describe the tilde data that I mentioned to get the median was basically getting that response, putting it into a pandas data frame and do a describe function, use the describe function. So nothing really hard, but to make the agent actually using the tools as intended was a bit of a struggle. And even now, I probably need to run the agent 5 times in a row to actually get the correct answer. So yeah, it does. It probably has to do with the prompt, probably has to do with the temperature of the model, but I was really excited to actually learn about MCP, so model context protocols, that would probably ease development of stuff like I just showed, where MCP servers are. You can see that as like a unifying API, because what I just showed you before is that my agent was having its tools in the same place and querying directly the API. So if the API changes, I have to change the whole thing. And it's very dedicated for a specific thing. And the way I'm using my tool is not going to work for another API that could query a database or that could actually trigger a process. But so what MCP brings is basically a standard protocol for the agent and the LLM to interact with these tools. So in the end, it doesn't need to know how the API exactly works. It will actually be able to discover and understand how to use the tools that are in this MCP server. So it's like a unifying API, but also like a toolbox. What I was very excited about is that I showed you before that we are using containers. And so my idea was like, oh, that would be great if we had MCP in containers so we can deploy that in ESNZ. And yeah, they are. And most of the tools or most of the things that we use every day are already there. So containerized MCPs for specific, Grafana, the dashboards, AWS Terraform or Kubernetes. So you could fire up your containers via just an agent like, hey, start this pipeline through Kubernetes, or retrieve that stuff from MongoDB, or plot this figure in Grafana. I think this is that kind of blew my mind. And just to give you an example of the GitHub official MCP server, just to give you an example of what are the tools that are inside these MCP servers. And you can see create branch, create gist, create issue. So everything you would do yourself, you can basically delegate that to an agent now. So yeah, that was a bit of me thinking about all we could do with that. And since I'm working in the JWASR space and the monitoring and supporting agencies, the National JWASR Monitoring Center here, I was kind of thinking about supporting response. So response is basically when a large earthquake occurs, or when you have a tsunami, or maybe a volcanic eruption occurring. So hopefully not all at the same time. But the first thing you will have to do is to need to assess threat. So it's a lot of information gathering. You need to assess the impact. So that will involve modeling. You're going to access different database of scenarios that exist already. Most importantly, you have to communicate between teams and then communicate to the emergency management. So that requires a lot of manpower, a lot of focus. And so that kind of, I had this idea making this talk that eventually we could arrive to that point where we are here. I mean, I'm basically here, one of them. And I need to basically gather information. I need to tell somebody, or somebody needs to run something, maybe a risk-ape analysis. Somebody needs to put information in a Slack channel. Maybe another one needs to pull a tsunami scenario, so an inundation map for the closest earthquake that's similar to the one that just occurred from another database. And we need to monitor some data from GeoNet, but also from international agencies. And so I kind of think that maybe in the future I would simply go on Slack and say, hey, agent, find the closest scenario from the tsunami database for this earthquake, and show the result in the response dashboard on Grafana. So basically, just talking, the agent would be able to catch what I want, infer which tool to use. So we are back here, infer which tool to use. Okay, it wants to pull the closest scenario from the tsunami database. It will use that MCP server, this API, this database, bring it back and send it through that MCP server to Grafana maybe. And then, yeah. So I think there is a lot of things we could do. We are going to be able to do actually with these agents and MCPs to support maybe response. But I think in terms of software engineering, now when I'm thinking about developing something, I might be thinking about how it could be integrated in a much bigger picture in some kind of a web where the agent is going to be the spider of that. that way. Yeah, I don't know, hopefully on time, but yeah, thanks very much. Hope you are as pumped as I am about this stuff.
Cool. Thank you, Flora. Got time for one quick question. Got one in the chat. You stated that agents struggled to use your tools. Is the issue that it didn't use the right tool or that it used it incorrectly?
I think, so I made the tool for a specific purpose. I think the problem was probably because I was asking it to use in the wrong manner. So I initially thought that agent could only pass text arguments and one argument, which is totally wrong now. I mean, I understand. But basically I was asking the agent to build a complete URL that would be able to, that the tool would be able to read. And yeah, that's wrong, because now the tool, I could make the agent to pass arguments that will be able, then that will be forming the URL inside the tool, and the tool can query that. So it makes it a bit easier and less prompt heavy, I think.
Cool, thank you.
Thanks so much.
Janet, if you start sharing your screen, I can introduce you. So next up, we have Janet Stacey, who is a lead senior scientist in digital and data for the forensic R&D team. She's a perennial learner. She has 2 Masters of Science degrees, one in forensic science and another in bioinformatics. Janet has worked in the forensic biology casework laboratory for 11 years before transitioning to a data science role. She's been in an active research software engineer for 6 years. Her work involves machine learning, AI, and automated workflows, experimental design, and data analytics, dashboard visualizations, and growing data science capability through mentoring and training. She's got a special interest in forensic intelligence, responsible AI development, and data lifecycles, including Maori data sovereignty. Most recently, she's begun her PhD in forensic science to further Bayesian networks for the evaluation of activity level propositions. Today, she's going to talk about automating the evaluation of forensic evidence. Over to you, Janet. Your microphone's not coming through.
Is that better?
Now we can hear you.
It's always the pull down the thing. Thank you for the introduction. This talk is covering what I'm going to be doing for my PhD. I'm at the end of my first year, excuse me. So don't expect too much technical description yet. It won't be as technical as the previous talk, even though that was amazing. Thanks. So yeah, my PhD is through the University of Auckland with supervisors of Sally Ann Harbison and James Curran from statistics. So for those who are not forensic scientists in the group, which is probably most of you, the idea of forensic science is to assist the justice sector by making sense of the significance of things that are found in the aftermath of a criminal event. But because we are investigating things in the past, it adds uncertainty. It's unclear from just finding something if it was there pre-existing, or if it's involved in the event, or if it's caused after the event from some kind of contamination. So we'll give you a scenario. So say the largest polished diamond in the world, which is pictured here, has been stolen from the museum. It appears that an intruder has entered via a window. There is broken glass found on the floor inside the window, and a blood-like substance is found on the case where the diamond was located. The blood is recovered and test positive with presumptive test for blood, so we can presumably call it blood. And from the sample, a DNA profile is obtained. It ends up matching Mr. J, who's pictured here, who happens to be a museum janitor, so he works there. He's arrested, and the power of the evidence is evaluated by the forensic science. The way we tend to do these things are at what's known at the source level or subsource level. Source level being, is the blood effectively, or is it something else that looks like blood? So is the blood the source of the DNA? Or we do it at the subsource level, which is the suspect the source of the DNA profile rather than someone else in the population? So the way we do that is a statistical evaluation using a Bayes theorem likelihood ratio, or odds ratio, where the prior odds are what's known about the case prior to the evidence being submitted to the courts. So whatever the judge or the jury know prior to understanding about this DNA profile. That could be other types of forensic evidence, or it could be circumstantial evidence, video evidence, other things that they've been told. The fact finder, so the judge or the jury, is responsible for deciding how the overall picture looks. So whether the suspect is responsible for the event, the offence, or if someone else is responsible for the offence. And as forensic scientists, we don't touch an offence level question. We don't say, is the suspect guilty of some offence? Where we sit as forensic expert witnesses is with the likelihood ratio. So we will talk to the probability of finding the evidence that have been recovered, in this case a DNA profile, given that the suspect is the source of the DNA profile, versus the probability of finding the evidence, the DNA profile, if someone else is the source. So it's a ratio, and it correlates into a very large number, generally at the subsource level. So we would go to court and say something like, the DNA profile that was obtained is 100 million times more likely if it came from Mr. J than if it came from another individual in the population. This is a conditional probability, so it has to be said in a specific way. But what's happening in courts in recent years is the defence counsel will say, my client works at the museum as a janitor. Hypothetically, is it possible that the blood you found was caused by an injury a month before the robbery? To which we have to say, it's possible. All we can speak to is the fact that the DNA profile is more likely to be his than someone else. We can't talk to how long it's been there, how it got to be there, which has become a bit of an issue, because saying it's possible isn't talking about likelihood of probability or plausibility. And we actually have a whole heap of knowledge in the literature, in forensic literature, that we understand how these trace evidences, whether it be body fluids, DNA, RNA, glass, fibers, prints, fingerprints and such, we know that there's a lot of literature around how they transfer from object to object or person to object, how long they persist in the environment, how commonly they're found in general, and when there hasn't been a criminal offence carried out. And we've kind of got a rate of recovery of how easy it is to obtain the findings that we've found, the metrics that we've measured from the evidence. So for example, for DNA, you have to swab it or lift it in some way from a substrate and able to extract the DNA and get a profile. Which the problem is that without that knowledge, it's left to the fact finder to interpret what it means that this DNA profile might have been left there a month prior. So, and often what's happening is that hypothetical scenario is given in court where there is no opportunity for the forensic scientist to actually do a literature search of the publications to find actual data to support some kind of statistical analysis of this. And often it's very implausible, the scenario that's actually given. It's got multiple transfer steps, or it's been submerged in water, or things like that. So while we're saying it's possible, it's really often at the end of, it's really unlikely to have happened, but I have to say it's possible because anything's possible. So we need to address this in some way. And in fact, that use of likelihood ratio is still a possible way to address these kind of questions. It's just our propositions change. It's no longer at that subsource or source level, it's now at an activity level. So it's, what is the probability of finding the evidence that we've had given that some activity has occurred? So in this particular scenario, the blood is from the time of the incident versus the blood has come from some previous period of time or a very long period of time prior. You can see where this blood kind of scenario can actually come into play in terms of sexual assault cases where someone has said they've had consensual sex a number of days ago and then been raped. Is the findings that have been found to do with the consensual sex or to do with the rape? So it's very comparable across different case types. This is known as activity level reporting or evidence given activity level propositions, depending on where in the world you are. And it basically is pulling in different sources of variation to what we look at for a source or a subsource level, subsource being how common are the alleles that we've found within the pieces of DNA that we've profiled within the population that is in New Zealand, for example. Whereas this would be more like those transfer and persistence kind of variables that I was talking about on the previous slide. There's also a consideration of bias, because to do this kind of work, you need to have a lot more understanding of some of those, excuse me, some of those extenuating circumstances within a case or other information that isn't relevant to obtaining a DNA profile, for example, where you don't really need much information at all. Ooh. That's okay. There is a way to do this. It's using Bayesian networks. They're visual, explainable, but at the moment they're being done in a case-specific way because of the dynamic activities that can happen or the dynamics of the case, and it can be difficult to find data. Globally, there's only a few labs that are doing this work for caseworks, and there's a lot of resistance in the community due to the learning curve of using and making Bayesian networks, limited avenues of where to get education to do so, no standards or accreditation, and that dynamics of caseworkers are concerned. There's also concern about whether a forensic expert should be doing this at all, whether they should be doing the evaluation or is it too close to offence, and who should be creating those propositions, whether it should have input from Defence Counsel, and how we describe error in our results. I've talked about bias already, and I've talked about the fact that training is a problem and guidelines and standards are a problem. So the way we see a way forward for this is to collate what we know about TPPR data, so that transfer and persistence stuff, into one place so that we can have a common place for people to start with their analyses, address the learning curve by introducing AI tools, implement only what makes sense for a particular case-by-case basis, because it's not fit for purpose for all cases. We just may not have the data, and try and collate those different types of evidence into one response, pull in the glass analysis from the glass that was found, etc., and address the gaps. So my PhD is doing these, which for this technical audience is not very difficult in terms of techniques. do a bit of a topic modeling of the TPR data that you can find, work out what the effect of different people creating Bayesian networks is, so how much variation there is in the output, create a vectorized graph database to store the TPPR data by similarity, and harness agentic AI to support it. So what that overall looks like is pulling literature from with TPR data, vectorizing it, storing it in a database, and then an agentic AI system where someone asks a question about their particular case. It retrieves stuff through a RAG augmented LLM and uses agents to build a Bayesian networks for the user. So my year one project's a lot of learning. I've done a literature review, which has just been accepted. I have recreated the Bayesian network not using a graphical user interface, but in R. No, that one's in Python, sorry. I've also started on the topic modeling using SBERT, sentence transformer, and hierarchical clustering to try and understand what's in the data that I have access to through public databases. And that's me. I won't talk about the arc sensitivity bit because it's not very far. Any questions?
Oh, thank you, Janet. Do we have any questions popping into chat, please? While people write them down, what's something that you've enjoyed the most about the year so far, Janet, in terms of what you've covered?
So I'm used to working on a lot of projects at once in my job. I'm obviously a mature student coming back to this kind of environment. I've really loved being back at the university, but being able to focus on one project 3 days of my week, because I am doing it in conjunction with continuing to work 2 days, has meant that I'm doing less projects at once, which means I can really get deep into it and find out all the answers. And also that, you know, just being able to do what I need to do or want to do within it has been really awesome as well. And a lot of great networking opportunities as well through the university. So
We've got a question from Emily. Could you talk a bit more about the questions of equity? Do you think these kinds of tools are likely to be available for defence teams as well as prosecutors of the state?
Yeah, quite possibly. So it's really strange situation where forensics kind of ignores a lot of equity stuff. Not that it, like, that sounds terrible. It's because a lot of the stuff that we deal with, we don't know where it's come from. We can't make any kind of pre-propositions that it's come from a certain ethnicity or a certain gender or things like that. So while we are looking into like gender diversity, for example, within forensic science and how that relates to the findings that we would find, when it comes to how we use AI for this space, it hasn't really been a factor. It's a little bit strange to say, but you are right in that a lot of the experiments that have been held about transfer and persistence have been based on certain subgroups of population because they're from the past. So it is something that I'm going to have to be very careful with when I'm doing this. And I'm also going to have to do some testing of the AI framework once I've built it, excuse me, to make sure that different people putting in questions, either from a prosecution or defense status, don't really affect the outcome, because that's the ideal, right? You would get the same result either way. So there is a lot of unknowns in this space, and I know I'm not going to be able to solve every problem, but I am aware of the issue of equity and very, very keen to make sure that I address it.
And one final question here from Brent. Do you have a feel for the potential scope of the AI agent's part, for example, using the agent to pull together information to answer a particular proposition versus positing propositions itself based on historic cases?
Yeah, so given the data that we have access to, because obviously past casework is very sensitive, I'm not going to have access to outcomes or case details for previous cases. So I'm anticipating this will be that the user will ask for a set of propositions to be assessed rather than the agents doing that. So the agents would very much be trying to extract the parameters that are required for probabilities to inform the Bayesian network tables, conditional probability tables, and build the Bayesian network. Because at the end of the day, a person, the forensic scientist here, is going to have to stand up in court and give their opinion on this evidence. Every forensic science evaluation is opinion evidence. So therefore, they have to be comfortable, and it has to be transparent enough that they know where that data has come from, how that has been made, and they are comfortable that they agree with what it's saying. So it's not taking away the forensic scientist's job, it's supporting them so they don't have to learn how to make a Bayesian network or a new software, GUI, that creates Bayesian networks in a way, and also enabling them to get as much of that transfer and persistence data as possible to inform it, because at the moment it's very ad hoc, it's not systematic in the literature searches that people do.
Cool. Thank you very much. And thank you to Florin as well for the two speakers in this session. According to my program, we're now on a break until 10:55.
Have I stopped sharing?
Yes.
Okay, thanks. I can't see it.
Okay, it's 10:55, so we'll get started again. Hello everyone, I'm Brent Martin and I will be the chair for this session. We have a packed session this time. We have 4 lightning talks and 3 main full presentations, so we'll crack on. The lightning presenters, you have a 10-minute window each, but I will put a hand up after 8 minutes so that you know that you need to wind up. And without further ado then, we'll get into the first talk, which is by Maxime Rio and his collaborators on PyEarth tools. Thank you, Maxime.
Thank you, Brent. Kia ora, I'm Maxime, and today it's my great pleasure to talk about a little bit about PyEarth tool, a package to lower the entry barrier to machine learning in earth science. And before explaining a bit more what it is about, I'd like to acknowledge my co-authors, Tennessee Lowenberg from the Bureau of Meteorology, and my colleague at Earth Sciences New Zealand, Gemma Mason. A bit of context first. In Earth science systems, we model all sorts of things like the ocean, the atmosphere, vegetation, ice, different spheres like atmosphere, hydrosphere, cryospheres, sometimes alone or sometimes in a coupled fashion. Until 2022, this was accomplished mostly with physics-based models, and you need a big computer and HPC to do that. It was quite computationally intensive. Then something happened. The machine learning models, they got good at it. And here I have just a few examples. On the right-hand side, you have ForecastNet, one of the first neural weather model based on Fourier operators, and that can do some global weather predictions. Then a bit later, you have Stormcast in 2024, which is using diffusion models also to do weather forecasts. And more recently from Microsoft, we have the Aurora model, which is a foundation model, something you can repurpose to do all sorts of Earth and system modeling at a global scale. So in this context, what is PyEarth tools? So PyEarth tool is an open source Python framework, which goals is to ease starting with this sort of domain of ML research for Earth science system. It has originally been created by the Bureau of Meteorology in Australia. It's available on GitHub. We also have a documentation on Docs. And now I'll describe in a few minutes the main components of it. So we have a data component, pipeline component, and models component. So the data API, so that's one first package whose responsibility is to fetch the data sources for you, and especially to abstract away how the data is stored on disk and in which format. And think about some of these data set, they have hundreds of terabytes of netCDF stored in a very particular way. But what we want is people just to import Python import my data sets, and then you have it. Voila, you can use it. So you don't need to care about the nitty-gritty details of how it's stored. For some of these data sources, the package will do the fetch and download for you, and from others, especially the big ones, it will rely on your nice HPC admins to store it in the right way, in the right place. But as a user, you just have to import the package, and that's it. This package also has some pre-processing routines, typical transforms like, for example, changing coordinate systems. On top of that, the thing which makes me very excited is the pipeline API. And what that does is, on top of the data sources I just talked about, you can stack a set of transforms of operations in a pipeline fashion. And this creates an iterator-like object in Python. And then you can fetch samples one at a time. And this is what you'll use to feed your machine learning model. There's a bunch of goodies on top of this. You can have branching. So if you want to pull data from multiple sources, maybe satellite at the same time as reanalysis data, you can do it. It also has some caching mechanism on disk. Some operations you can undo them. Think about normalization, for example. And it's very nice in a pipeline that you can, after doing the training and the prediction from your model, you can undo some of the transforms and you have your data converted back in the original space. And it has a nice and convenient serialization format, which is a configuration-like format to share your pipelines with colleagues. On the right-hand side, you can see one definition of a pipeline with the data sources for the WeatherBench2 dataset, and then we apply a set of transforms, and you have the graphical depiction of it on the bottom right, which is the same pipeline. And then the last elements of the toolbox will be the models themselves. And here there are two pieces. One is the package that will do the translation, the bridge between the pipelines and some particular machine learning frameworks to help feed data and train models. In particular, we support PyTorch Lightning and HTBoost. And in a separate package, we also have a zoo of models. And here is the goal is to have predefined models, so you don't need to write yourself in PyTorch actually how to do a forecast-net model, but this is pre-made for you, and you just have, with air quotes, have to put the data in it to train it, and then you can run inference. In particular, we provide a forecast next, which is a variant of forecast nest I was talking about earlier, and Lucy, which is a climate model. And the right-hand side, you can see how to call such a model. Again, it's a matter of importing it from the package and feeding it the data. And that's it, that's done. And you can see a global prediction of a 2-meter temperature on the bottom right. So for you, sorry, how to get started with it? Well, I would really recommend to have a look at the tutorial gallery, and there's a ton of examples there. And in particular, one thing which is nice with this toolbox is we have some tutorials targeting lower hardware requirements. You may still need a GPU, but a gamer GPU will be good enough to get started and get an idea of how these models works and what you can achieve with them at the lower resolutions. And of course, you can scale to higher resolutions. And if you have an Apple device, we also have a specific demo which is targeting this sort of hardware. And I'd like to conclude by saying a few words about the open source aspect of the project. So you have on screen the list of contributors from all around the world. I've been very lucky to work on this project thanks to the Momentum partnership, which paid for my time on this. And yeah, we'll welcome everyone to come and work with us, and maybe next time we display this slide, your name will be on it. Thank you, everyone.
Thank you, Maxime. Excellent talk. People, feel free to put your questions into chat. We've got about a minute for questions, or you can unmute and ask Maxime a question. And while we're waiting for a question, one from me. This looks like it's a really amazing tool. Is it something that's already being used in anger? Is it like, what's the maturity of it in terms of use?
So as I said, the tool originates from the Bureau of Meteorology, and we know that it has been used a lot there. But what you'll see is what has been part of the open source translation. So maybe what is now available has various level of maturity, but it has been used internally at the BOM a lot and with great success.
Great. Anyone else got any questions they'd like to ask Maxime? Okay, if there are no further questions, thank you again, Maxime, and we'll move on to our second lightning talk, which will be from Hugh Sorby, bringing together research development, develop software and software engineering principles.
Right, thank you. My name is Hugh Sorby, and I work as a software engineer at the University of Auckland in the Auckland Bioengineering Institute, or the ABI. The ABI is a large-scale research institute at the university, and this is similar to a university faculty, except that it doesn't have any undergraduate students. So all the students at the ABI are at the postgraduate level, and they have already learnt the code handling skills that they are going to use for their research. So today I just want to start off with setting the scene and then talk about the different worlds of a researcher and a software engineer. And then I'd like to share my observations on the gap between research software and engineer software and how we can bridge the gap. And then I'll give some final thoughts. So for context, the research undertaken at the ABI really stretches between the medical and the engineering disciplines, all in a biological setting. The IBI is structured into several research groups. There is a medical devices instrumentation group, a biomimetics group, an augmented human technologies group, and a computational and experimental physiology group, which can be split into several smaller groups, roughly divided along the organ systems. So I work in the computational physiology group, and it will probably be evident that most of the work done in this group involves developing applications, models, or scripts in software. Whilst Python is de rigueur, we do have a lot of Fortran and C code that has been developed, both historically and currently. And we also do some development in JavaScript, but that, by and large, is done by pure software engineers. A lot of the software written by researchers only lasts for the length of time that they are studying. Rarely do we see code handed over and built upon. And I believe this is mainly because of the difficulty in understanding the code and getting it working in another development environment. So that's our context. So the way I see it, there's two worlds. And the research software is really got one simple aim, and that is to publish their work. They will write very procedural code. They will focus solely on that goal, and they'll try and get there as fast as they can. They're not concerned with testing. The testing they do is the testing that happens as they work on their code. If they're not getting the correct answer, they will change the code till they get the right answer. They're also not concerned with maintainability. They're working on it until it is finished, so it's always current, so it doesn't need to be maintained because it is as active at the moment. Quite often we find that the researchers don't update their computer. They will endeavour to keep their development environment as static as possible. It will reliably work for them on their computer. And it won't be scalable. So other than being able to say it can run, it will be completely the opposite of what an engineered software should be. These statements, of course, are not true for all software written by researchers, but I find it's true for about 95% of them. So once the researcher has their code working on their machine, this is really the most likely time that I am come into the picture. Sometimes I get involved in helping sort out the odd bug or two or installation problems, but quite often the first time I get asked to look at a researcher's software is when they have it working on their machine. And the conversation typically goes something like this. And I find I quite often have to remind myself that researchers are not interested in software engineering. That is something that I am interested in, and it's not their driving interests. And they also do not want to learn software engineering techniques. They want to get their paper published and get their software supporting their research. So did it become hard to convince someone of the benefits of a certain path when an individual can only live that one existence? Without a tangible benefit, it's hard to convince someone that someone to do something they do not want to do. So we need to compromise. I need to compromise on my standards of software engineering that I like to live up to, and I need to get the researchers to take a little time to lean more towards the software engineering side of things. Some of the interesting things that you come across when looking to bridge the gap are things like having hard-coded paths written into software. This one is usually fairly obvious, and it's a pretty easy sell to get hard-coded paths removed, which I find often becomes the first step in creating a bridge. In a Python setting, I do try and encourage the adoption of PEP 8 guidelines, and the uptake I find is heavily correlated to the amount of code that has been written. If I can't get the full PEP 8 conformance, my fallback is to try and get at least the function names looking like they're Python. Code management is another area towards getting some software engineering going. In the past, passing around zip files has been quite a common thing to do. So trying to encourage people to actually track code changes. This over time has become less and less of an issue as more people are using Git. But using Git in a manner that a software engineer would use it is still a work in progress. With luck, at some point, I'm hoping we might get some commit messages that actually indicate what changes have been made. And one of the further things I like to try and get people to do is trying to implement some sort of Git flow development process, something with pull requests, somewhere where we can get some CI and some testing running and some code checking going and review process being followed before that code gets merged into some common upstream repository. So my conclusion about this all is I don't find it very useful to explain how to go about making good code available through a package manager. I found that this sort of task is much quicker if I do it myself. Most of the software that researchers create is never going to be used in a production environment. Therefore, we don't need all of it to be good. The general standard of code, I find, code management at the ABI is poor, and I would like to raise it. I'm firstly aiming for a reasonable standard. I think good is still a stretch too far. I also think bringing together may be too strong a term. I'm thinking we're looking at really a tenuous link between the research software and engineered software. Now, we don't need something that is whiz-bang from the start. Just like when we develop software, we need to get something out there and then start improving it. One of the areas that I definitely think we could be improved is pointing people towards the software carpentry courses to raise that basic level of knowledge around the basics of software engineering. And I do see that going forward, needs to be a partnership between the researcher and the software engineer, with both focusing on their strengths and being able to open to compromising on the changes required to create a better software product that lasts longer than the lifetime of the research paper or study. Thanks for listening.
Thank you very much for that, Hugh. Sorry. Anybody got any questions that they would like to unmute and ask Hugh, or
I have a
refer into
question.
the chat? Yep, go ahead.
Hugh, thanks. Good talk. It seems like you have a pretty dim view of the quality of researcher-written software.
It's more. It's just to be clear. I wanted to say it's more around what I experienced in the ABI.
Yeah. No, I think a lot of people would agree with you. I'm just wondering what you think about, in terms of many science researchers not really being interested in engineering their software better. I wonder if that's actually not really acceptable anymore. Can you rely on computational research results if the code is not, reproducible and discoverable by others? I mean, arguably that shouldn't be allowed anymore.
Yeah, I think. I mean, I obviously am being a little bit harsh there, leaning towards the harsh side. But a lot of the computational code that we use is in particular in the ABI is very legacy code. And it has been used for a long time, so we have that trust in it that has been built over the 30 years it's been in use. It is definitely difficult to use the particular computational software that we use. It is not easy to reproduce results. But we do endeavour with some of the things that other projects that I work on in CellML. We are trying to make this situation better. And I think we are improving that over time. But really, I think because of the nature of the students that come through and they're transient, if you like, they don't really have that time to learn that second discipline. Some of the good ones do. They've got the capacity to do their PhD and learn some of these software engineering techniques and capabilities, but not all of them have that ability. And all this driven by interest as well. Their interests just don't lie in that software engineering viewpoint.
It's a difficult problem.
Yes.
Thank you.
And I think it's a long term. I see it as a very long term process where getting it on the ground with our younger associate professors and getting them to instill it into their groups. I think we're slowly seeing an improvement in that area where we've been working with these researchers, more of the long-term ones for longer, and it's slowly seeping its way down through their groups and being passed on to their students. So I think that is improving, but it's a long process. It's the evolution of early career PhD to early career to associate professor and professor is quite a long time scale. So we can't be thinking this is going to be fixed next year.
Yeah. Thank you very much for that, Hugh. We're out of time, so people can continue with questions and comments in the chat. Thank you very much. We'll move on to our next speaker, which is Tom Kelly, Build It and They Will Come, a story of the Leiden R package.
Okay, I think we can all see my screen. So for our next talk, we're going to talk about research written software. But there's, I think, some good points raised here. I am obviously leading by example in this field, and I hope it does inspire others to follow this path. But as discussed, this is still quite an exception, I think, for a researcher to really get deeply involved in this. The example here is actually quite simple. It's an interface between R and Python, but it's been useful to many people. And Brent and I are actually now colleagues in the BSI, thanks to our merger. But I'm going to talk about my previous work as a postdoc in Japan for several reasons. The first one is it's more relevant to the topic of the meeting. I'm not currently in a formal research software engineer role. And the other is there's been time since this work was done to really see the impacts, which I hope inspires others to try it out. I'm going to embrace the Japanese tradition of introducing myself first. So I'm actually originally a mathematician as well as a geneticist, and I'm still to some extent a geneticist today. This work was done when I was in Yokohama. This is Yokohama here, quite close to Tokyo down here. and quite a stimulating interdisciplinary environment. We had people working on genomics, immunology. I was mostly a bioinformatician, but had to build much of my own software as we went about it, which did carry on quite well into my career in both the private sector in Japan and now the public sector in New Zealand. But most of that corporate work is protected by IP, and I'm quite new in my current role. So I'll talk mostly about working on this lead algorithm. For those of you not involved in clustering, the joke here is that the previous method was called Louvain, after the town in Belgium where it was developed, and a group in Leiden in the Netherlands developed a successor to the algorithm. This is also quite interesting in terms of disciplines, because these were social science researchers trying to find communities in a social network, but at the time we were working on single-cell transcriptomics in the life sciences, and it's really been picked up there. So their motivation was that the Louvain method is great because it's unsupervised and doesn't assume how many clusters there are, but it has a flaw where if you're randomly picking a node and deciding which cluster it's going to be in, you can split an existing cluster in half and lead to artifacts in the result. What they did was add a second step, so you're randomly moving the nodes just as in the previous algorithm, but there's also a refinement step where you basically do a sanity check of, are these communities still connected or not? It turns out that doesn't just resolve this issue, it's also faster and converges on the answer, as well as, of course, they developed it more than 10 years later, so it's just more efficient in terms of technology. And the downside is it's only available in Python and Java, and most people in my field use R. Don't judge me, my supervisor is a statistician. At the time, this is around when I was developing it, R was soaring in popularity, especially in the life sciences. And so my motivation was mostly, can I use it in my field and in my workflow? But there was, of course, many other people asking this as well. This is someone else asking the developer, who has been great at answering questions, both on GitHub, we send questions to each other when it comes up on our implementations, and of course on social media. So my main motivation here was to speed up my in-house analysis instead of context switching between R and Python, and to adopt this new method, which at the time was only on archive and available in Python. And I'd been looking at using the reticulate wrapper to call Python from R for a long time, so this seemed like a great opportunity to jump into it. What I did was use the DevTools and Roxygen packages, develop a package from scratch. There were helpfully some examples on GitHub of a similar purpose in the same field. And now this is released on CRAN and has been endorsed by the original developer, as well as by request at a conference, integrated in quite a large package. They now use a native R solution. But for several years, they were calling mine. And so you can see here, it has, over the past 5 or 6 years, had more than 1 million downloads just from the main CRAN mirror. Bearing in mind at this point, I wasn't developing it for anyone else, it was purely for my own purpose. So my take home is to seize any opportunity to learn new skills. Bear in mind, at no point in my career have I been a full-time software engineer. But through communities like this, and I was quite involved in this community before I went to Japan, I learned these tools, as well as avoiding premature optimization, avoiding reinventing existing tools. And yeah, I hope it inspires other people to try the same. So thank you, and I'll open for questions.
Thank you, Tom. Does anyone have any questions they would like to unmute and ask or put into the chat? I'll just make a comment about the avoiding the premature optimization. I found that an interesting one, having taught software engineering many, many years ago when Agile was new and there was the concept of YAGNI, well, you ain't going to need it. You don't build anything before you're absolutely sure that you require it. So I think that's an interesting observation in this context.
Yeah, it's also been helpful in terms of the community. I found the sooner I share it online, that the sooner people come in with suggestions, and then I say, sorry, I don't know how to do that, but I'd love to. And there's people jumping in with pull requests and helpful, usually positive, constructive feedback, building each other up. Been great. It's especially the art community's got quite a unique culture around it.
Yes, I guess that is a one of the things that comes up when you start doing shared and collaborative software development, is how you find that line between not having the more people you get, the lower the quality becomes, or the more unmanageable the code becomes, versus trying to keep people engaged and have people not feel fear that if they put things up, it's not going to be good enough and they're going to get somehow shot down. Have you had any experiences around that?
Yeah, that's one of my other projects. We had two of us working on it quite closely together, but it ended up being quite successful. We actually containerized that one with Docker. This was part of the same project, but I led this on my own because it was basically a means to an end to build some sort of side component that I could use in multiple projects. But yeah, collaboration is of course very important.
Okay, if there aren't any more questions, we'll thank Tom and we'll move on to our final lightning talk,
Yes.
which is going to be Jen Andrews, from Science to Operation within the Rapid Characterization of Earthquake and Tsunami Program.
Thanks, Brent, and thanks everyone. Hopefully you can just see my slides at this point. Great, thank you. Yep. Hi everyone, I am Jen Andrews. I am a seismologist at ESNZ, formerly GNS. Science to Operations for Rapid Earthquake and Tsunami Response represents the work of a large research program. And so there's lots of names on here, including Florent and Christophe, who you've already heard presentations from throughout this conference, as well as many collaborators, both within the organization and across international organizations. This program was led by Bill Fry and Anna Kaiser, so thanks to them too. And if I was to add a tagline to this presentation, it is an experiment in enabling scientists, so very much not software engineers, as we've been hearing about all these challenges in the previous presentations. It's about enabling the scientists to operationalize software tools in order to achieve scientific aims and real-world benefit. And so this is sort of the story of our journey and some of the lessons and some of the challenges. If I can. So just to introduce the RSET program, or RSET just stands for Rapid Characterization of Earthquake and Tsunami. It's just ended. It was a 5-year large public initiative to better prepare for and respond to natural disasters in New Zealand. The motivation for this piece of work was that robust, rapid and automated data analysis and information dissemination can really play a vital role in mitigating impact and accelerating recovery during these really large geohazard events. In terms of the specific aims, there's a couple, the two main ones are up here on the screen. So for earthquake, it was about faster and more accurate earthquake source and shaking information. And so for these, you're thinking local and large, so events like the Canterbury 2010-2011 sequence or Kaikoura in 2016. The other aim around tsunami was faster and more accurate tsunami forecasts, this time with the regional lens of Southwest Pacific earthquakes, so things like Hunga Hapai type events, but earthquake driven. And this is tsunami early warning in the sense of it needs to be fast and accurate enough information to enable timely and targeted evacuation of populations at risk. So one of the key aims of the program was to test and operationalize a suite of rapid scientific characterization tools in order to reduce the time taken to understand these geohazard events and the hazard they pose from hours to days, which is what we'd seen in the past, 2 seconds and minutes, so that this information really does become actionable in the response setting. The program as it stood sits within a broader response landscape within ESNZ, parts of which are much more long-term than RSET. RSET was this finite program over a few years. And this slide just speaks to that. So over on the left-hand side, the program is building very much on top of the work that GeoNet does. So the GeoNet program, hopefully that's a name familiar to everyone. It's within ESNZ. It's responsible for installing and maintaining these data monitoring networks. Seismic, geodetic, and water level are critical to our RSET program. And it's very much about business as usual as well, geohazard monitoring, so that continuous 24/7 monitoring that Florent referred to, and it works in that space of production level tools, high resilience, high service level. On the other end is a whole set of people in our response science pipeline, so duty officers, expert panels, science advisors that are feeding information through to emergency management sector and the public for decision making during large events. And the RSET program is this big block in the middle that was aiming to build on GeoNet with the acknowledgement that in the case of very rare or relatively rare, complex and highly damaging events, we need more data and analysis than just business as usual to fully comprehend an event and its potential impacts. And many methods and tools arise in the research space continuously to provide this richer information. And those tools evolve quickly as new techniques and technologies develop. So the challenge for us was to have a set of these specialized tools that were well tested for the region, available automatically and reliably and rapid enough that we can be using them in geohazard response currently, but also that can be in a framework that can be updated and replaced easily as methods are superseded. And we also need to daisy chain some of these together into pipelines to facilitate a range of analyses. So we worked through this problem, standing up these tools on local infrastructure and platforms. And this slide just speaks to the operational aim and some of its challenges. So we were aiming to take a range of scientific approaches and provide a pathway to test and implement them in order to achieve real-time, mission-critical, and extremely rapid, so that's seconds to minutes operation. One of the main challenges is we were picking up tools that had different levels of maturity. So we had both existing international best practice methods that other institutions have running in real time, but also developing novel techniques from just initial ideas here within the organization. All of those then need to be written, tested, and tuned for the New Zealand context and tectonic environment. And then the endpoint for the tools could sometimes be different. So sometimes we were working on a manual tool that needed an expert to be able to pick it up in the case of a minutes after a big event, run it and produce some output that they could feed forwards. Other tools needed to be fully automatic and be producing these results and sending them out, disseminating that information completely automatically. We needed a pathway that was going to be broadly similar so that the operationalization piece wasn't a huge part of the effort, both in terms of time and resource and learning curve, because we were doing all this predominantly with and by physical scientists, so people with varying degrees of software experience. So none of them, or very few of the team, had computer science, software development, or IT backgrounds. We had a few things work in our favor for this program. So RSET coincided with some wider organizational efforts to implement a development platform, so to provide some key tools that were going to support software development for the physical scientists. And those tools sort of fit all the way around the software development cycle. And RSET could really pick up and leverage these, and we also fed back in terms of contributing additional ideas for tools that would help in the future. And obviously, we're providing testing along the way. I've highlighted here just a few of the tools, and I want to just speak to sort of how they helped us in terms of what we needed operationally. So because these tools need to be running robustly and reliably in case of those geohazard events, tools like code repo management, CI/CD pipelines, artifact and container management are critical in terms of helping that goal. We also needed real flexibility, and so that's where containerization became our friend Florent spoke to that as well. We're using Docker, but we were picking up tools in such a range of programming languages. We've got some in C and C++, no doubt. There's some Fortran under the hood there, Java, all the scientists' favorites, things like Python and MATLAB, and then some really niche tools that were written in TCL scripting languages and things like that. We needed to pick them up and use them very quickly, trying to reduce the time and technical obstacles to getting these up and running, and to continue to allow our researchers to work in their preferred languages. So we were also sharing tools and experience and knowledge, things like templates and best practice as well, to try and support each other in this endeavor. In terms of achieving automated pipelines, we needed communication between tools. This is to exchange information automatically and also to trigger operations. So we actually chose Kafka for this task to link tools that were driven by the continuous data streams that were coming in, and also downstream to some more impact-oriented tools like shaking and tsunami forecast tools that are just driven when an event has occurred. But we also wanted to write that communication layer as a really lightweight wrapper so that it could be replaced easily. We didn't want to build it into the tools directly. And then finally, in visualization and dissemination of results, again, picking up things that were hopefully easy to use and easy to start. So things like Grafana dashboarding and Plotly Dash to be able to send things out to our response scientists. And so to wrap up, this is just a summary of some of our experiences, the opportunities and challenges. So we did end up building this ecosystem of response tools. They are implemented. They are currently being used in geohazard response. As I mentioned, we benefited hugely from having this underlying platform that was being supported, that we could leverage and feed back into. But hopefully we were taking on at least a little bit of the good software practice in terms of sharing information, so avoiding duplication and building sort of lightweight layers. Some of the ongoing challenges, it remains an issue to co-develop and to share data, especially with external partners, and navigate security challenges. It's still challenging to support and enable scientists who are coming in with a range of skills, experiences, and interest in this kind of technical challenge. And obviously, the biggest challenge will always be the long-term maintenance, development, and support of these kinds of systems. And I'm curious if this community has any ideas on what we could have done better, faster, easier, and other experiences. Thank you.
Thank you, Jen. Would anybody like to jump in very quickly? We might have time for one quick question or comment. Okay, if not, we will now move on to our three full presentations, starting with welcoming back Maxime Rio, who's going to talk about simple tools, quick wins, and big gains.
Can you see my screen? All good? Yeah, okay. Tēnā koutou katoa, ko Maxime Rio. How? And yeah, I'm back. So it's my great pleasure today to take you on a tour on about 3 simple tools I've been using over the past year. They really saved my back, and I hope you'll find them interesting. Before that, just a few words about myself. I'm a data scientist at NZRSE New Zealand. I work on HPC platforms with and for scientists, and most of the time I design, implement, and optimize all sorts of data pipelines and machine learning models. I'm very happy today because that's my 5th NZRSE conference. I love this conference, and this talk is my way to give back to the community about what I like in terms of tools. And also I like some chouquette pastry, as you can see on the right-hand side. Okay, so I'll talk about 3 very different tools and no relationship with together, so it's a bit of a mixture of a talk. The first one is Pixie, the second one will be Git filter repo, the last one is GNU Parallel. Apologies in advance, I'll be speaking maybe a bit fast and there's a lot of text on the slides. Fortunately, there is a recording. Okay, Pixie, what it is, it's like Conda, but just better. And in a nutshell, so it helps you to manage environments of packages, self-contained environments of packages that you can use to support yours. Your project. And one key difference for Pixie is that it's project oriented and you can handle multiple environments and in one configuration files. It has tons of good defaults in my very own opinions. One of them, for example, is all the environments will be stored in the local project folder, not in your home. Very important if you're on an HPC system. It's reproducible by default because it maintains a log file. I explain in a second what it is. And it's really fast. And if you combine these two features, it means that you don't need to keep around your environments. You can just trash them when you don't need them and recreate them on the fly. As an example, I have a 12 gigabyte environment for machine learning, which I can recreate under 1 minute when the package cache is warm. Also, it integrates very well with standard Python packaging configuration. I have an example in the next slide. Has cool support for task. It's super easy to install. It's literally a 50 megabytes static binary executable, and you can use it to support global tools management. I won't talk about this, but it's very cool. I really encourage to have a look at that. How to get started with Pixie? On the right-hand side, you see a few examples of commands like initialization of a project that will create these pyproject.toml files. In that case, I'm adding few dependencies, numpy, scipy, matplotlib. It will record the exact versions I'm using. Then instead of doing a conda activate here, we're spawning a subshell, and bam, we have Python installed with our numpy, and that's done. As an example of how it combines well with the package, the configuration files, the pyproject.toml files from Python package. I have, for a given project, I have my dependencies. This is standard pyproject.toml syntax. I have optional dependencies for notebooks and another type of optional dependencies for development stuff and automatic speech recognition. And here's the magic with Pixie, which is in the bottom right. I created 3 environments. The default one, which will reuse my default dependencies plus everything about notebooks and development. A production environment where I leave out the notebooks and the dev, and then the one about automatic speech recognition. And extra bonus for the development, for the default and the production environments, I have the same solve group, which means it will, under the hoods, install the same versions. So we won't suddenly jump to a different version of NumPy when we turn to the production environment. I was talking earlier about the reproducibility out of the box. So this is handled by these Pixie log files. Every time you install a package, well, it will record the exact versions you're using on your machine alongside the hashes. Very important in these days of supply chain attacks. It supports conda and PyP packages. And literally, if you give these pixie.log files to your colleagues and the pyproject.toml, they can reproduce in one simple command all your environments. So yeah, that's very neat. Finally, I'll say a few words about tasks. So sometimes when you're developing a project, you have all these sorts of little scripts, or maybe you have a makefile to run your checks or run your tests, build the documentation. In my case, I usually have a little something to install Jupyter kernels. You can put that into the configuration of Pixie and with a bit of documentation so that it's become self-discoverable via the Pixie command line tool. And this is what you see on the right-hand side. My Pixie task list command will actually list everything which I've been defining in these configuration files for anyone else who wants to run the formatting tool, for example. And bonus, on top of that, you can define these different tasks to activate certain environments. As I said before, it's a multi-environment tool. Okay, so that was it for Pixie. Next, we'll talk about Git filter repo. So nothing related at all. So for that second tool, imagine that maybe by mistake, you've been doing your Git commits and suddenly you committed some credentials or some very large files. And worst of all, you pushed that. Okay, that's a bad time, but you can still do a few things. The important thing to know is the Git history is immutable by some aspects. So you can, of course, revert the commit, but the problem is this will undo your change. It will not sort of rewrite the history of the commits to remove these credentials. You can use git rebase or git amend to maybe change the very last bits, but if your change impact multiple branches, it will be complicated to do that. So my advice here will be actually, well, probably remove the whole repository, tell your collaborators, also change the credentials that have leaked, and then use a local tool in your local clone Git filter repo in that case to rewrite the history of the repository without the problematic contents and push back the new repository. So what is Git filter repo in more details? Well, it's a simple Python 3 script. You can there are ways to install it, but you can literally clone it or copy it from Git and put it in your folder, and that works. It can replay all the commits on the different branches and apply some sort of filters. The nice thing with Git filter repo is the simple cases are made easy, and there are some on the right-hand side of the slide, which I'll explain in a second. But if you need to do more advanced stuff, you have ways to call callback functions. So here are a few examples. Let's say you want to remove a particular file from your repository. You can select the file using the path indicator, and you can say, actually, I don't want that file, so you invert the paths. Another typical use case is, whoops, there are some big files, and we don't want to store big files in Git repository. There are other techniques for that. So we'll actually remove every blob, which is more than 10 megabytes. And finally, maybe there is this case of the password which has been saved in a file. So you can run some filters which will actually change the content of the file stored in the Git blobs. You need to create a little expression file and say, okay, this is the string you will find and remove, or you can even specify something to convert. So if it's foo, every time it finds foo, it will replace it with bar, and you call it this way, and it will do the job on the whole repository. How I've used it. So for my use case, we had a repository having 10 gigabytes of netcdf files, which have been committed. They were in multiple commits, in multiple branches, multiple versions. So it was actually interesting to replace the whole history, but remove these netcdf files. And what I wanted to achieve here is to store these netcdf files in another version control system tool called DVC, which is dedicated for data version control. Won't go into too much details here, but long story short, it will keep the information, the metadata, as a file that you can store in your Git repository. So the goal here was find all these netcdf files, replace it with these .netc.dvc files. And to do that, I use the callbacks I was talking about earlier. And that relies on having a little Python snippet or the body of a function that you call. So here on the right-hand side, we have two filters. First one is I just doing a simple rename. Every time it finds something .nc, it replaces with .nc.dvc. And then the other one, which I won't go into the nitty-gritty details of it, but literally every time it finds one of these files which has been renamed, it will use the content and put it in DVC with doing an external call to process call, and then from DVC it will take the metadata information and inject that into the blob, and done. The script is a bit longer, but that's sort of the gist of it. Okay, I'm on time. Yes, I'm on time. Okay, so the last one for today is GNU Parallel, another fantastic tool, and which if you don't know, it's one that I think will be very useful in many situations. So what it is, it's a Swiss Army knife for parallelization. It's a portable Perl script. We don't need to know that it's Perl actually. It's just a command line tool, very practical to do parallel processing. It has some nice dedicated syntax to combine sequences or handle file paths. I'll show an example in a second. And on top of that, it has many goodies, which you may not need to use, but if you have outside of the basics use cases, they're there. And the documentation is just wonderful. They have some tutorials, some examples. It's really nice to read. So a few examples. Let's say you want to convert some JPEG you have in a folder, and using ImageMagick, you want to create thumbnails. You can do an ls, for example, to get the sequence of your JPEG, and you pipe that into Parallel, and then it will run the conversion using as many cores as possible on your machine. And here you can see the curly braces are actually placeholders that will be replaced by the name of the file for every Parallel invocation of the command. The second line is an alternative syntax where you can do the same with these triple colon indications, and then you give the list, and it performs the same as the one above. The second example here is to highlight this sort of nice quality of life things from GNU Parallel. Is here I'm trying to convert all my Markdown notes in PDF using Pandoc, and what this second curly braces with a little dot in the middle do is it will take the name of the file but remove the extension, and which is something it's nice to have it out of the box. And there's many other ways to extract the folder names and things like that. As I said before, you can combine sequences and so do a Cartesian product. So here in this simple example, I have a sequence of 3 numbers and 2 letters, and it will run all the parallel tasks for every combination. And here the placeholders now have a number to know from which sequence it's coming from. How I've used it? Well, let's say that recently we had a rather urgent large data transfer to do between an old HPC platforms and a new HPC platform. And one of our colleagues had 110 terabytes to transfer between these two sites over almost 2 million files. And we wanted to use rsync to the data transfer. And the strategy we ended up using was to do a nested parallel strategy, which actually is a nice pattern to know even outside of GNU parallel. So we took the big list of almost 2 million files, and I created mini chunk files with only 5,000, the list of 5,000 files each. And that one, using GNU parallel, I was parallelizing across different nodes. So GNU parallel could access via SSH the different nodes. And then on each node, I use another GNU parallel, so another script, which was processing all these rsync commands, 30 at a time, in parallel on a given node. And overall, it took about a day to do the whole transfer, and we picked at 6 terabytes per hour using 9 nodes, and that was very practical. If you want to see how that looks like under the hood in terms of programming, on the left-hand side, we have sort of the outer loop parallelism across different nodes. And we have this SSH login file that tells GNU parallel, hey, by the way, you can SSH to this node, this node, this node, this node to do your task. And on these nodes, you will run this rsync chunk bash script. And that's what you see on the right-hand side, which is the inner parallelism with GNU parallel. And this one will be processing the 5,000 rsyncs from one of the chunks files. Nice additional goodies here. It's using a bash function, and you can pass that to GNU parallel. Okay, it was fast. So a little conclusion. That was my tour of the tools I'm using in my RSE toolbeds. There are many others, but this one really was a highlight of this year. I found them very useful, and I hope you'll find them useful too. Thank you. Tēnā koutou, tēnā koutou, tēnā koutou katoa.
Thank you very much, Maxine. Very interesting, and I'm sure lots of people will find all that super useful. I'm just going quickly to the chat. First of all, there is a comment from Libby Lee suggesting that, I presume it was the first one, Pixie looks similar to poetry. Do you have any comments around that?
Yeah, the difference between poetry or UV also is a nice one for Python, is that it will handle conda packages, so you are not restricted to the realm of Python packages. But if you want to install GraphViz, for example, to make graphs, you can have it out of it. So it's a larger sort of set of dependencies you can have access to. In my case, it's very Python focused, but you can do things in other languages or other utility tools.
Thank you. There's also been a bit of a discussion here around a question which you might like to weigh in on. That's about Pixie's licensing and how does it handle the licensing of Anaconda? Is that something you've had issues with?
No. So, but the thing, I know this situation can be confusing, but so the Anaconda licensing is with regard to the repository of packages. And Pixie, the same as Conda or Conda Forge or Mamba, you can redirect to another source of packages. And in that case, out of the box, we use Conda Forge. So there's no licensing issue with regard to Anaconda.
Okay. Thank you. And a cheeky question from Murray. When is the next workshop on these tools?
Okay, we can talk about that. Oh, by the way, I'll take this opportunity to thank the Hacky Hour people at NZRSE New Zealand, because this crammed 15-minute talk were actually 3 1-hour rambling that I did for them. So you had the short version.
Okay. Anybody online who wants to unmute and ask any questions or offer any comments if they've had any response with these tools? I see we've got another question from Tom Kelly. Curious if you've tried using UV or Nix?
No, and I'd love to. So for people who don't know, UV is a new package, sorry, a Python package installer, a bit similar to pip, just way faster. And interestingly, and it's written in Rust, and Pixie use UV under the hood if you need to install packages from PyP. So you're sort of using UV without knowing when you're using Pixie. Nix seems to be sort of the next step in terms of controlling everything with configuration file and hardcore reproducibility. I'd love to have the time to learn about it, but Pixie was sort of a nice trade-off for me to get 99% of reproducibility without learning a new programming language that will be required for Nix, for example. But I'd love to see people presenting about their use case of Nix in the RSE world.
I could ask you a meta level question. This is really about how you operate in this space. I mean, even just within this talk and talking about those three tools, there's bubbling up a whole bunch of other interesting tools that people have used that are alternatives. How do you personally, given that you are a really big user of tools in the technical world, how do you manage that? Do you do sort of like when you're looking for something new, you do a really broad search and evaluation to come up with the best tool, or do you tend to have to do something a bit more sort of random walk and rapid to cope with all the tools that are out there?
There's probably a bit of both depending on the time I have. And sometimes what happens is I hear about a tool and I look at sort of what's the status of that tool in terms of, is it very alpha or is it a bit mature? Disclaimer, Pixie is really usable even if it's below version 1, but it's changing quickly. Sorry, little digression. But then what happened is I think I keep in the back of my head all these cool tools, and suddenly sometimes there is a project that needs some help and I think like, oh, I can use that tool. That can be a good excuse to try that tool. And most of the time it works well. At least no one complains so far.
Okay, very good. Thank you for that. Anybody else got any questions or comments? If not, thank you again, Maxime, and we'll move on to our second full presentation. This is from Paulus Lohr, who will be talking about the deployment of a radio astronomy software on HPC using container technology. Thank you, Paulus.
Thank you, Brent. I hope my screen is properly shared currently.
Yep,
oh,
thank
thanks
you
so much, because I had a problem earlier. Thanks. So this talk is about the deployment of radio astronomy software on HPC using container technology. Let me just, first of all, I'd just like to acknowledge the traditional owners of the land that we are all meeting today. For my case, it's Bunurong people of Kulin Nation, and pay respect for their elders, past and present. And first of all, I'd like to introduce, for those who don't know, I'm working in the project called ASCAP, which is Australian Square Kilometre Array Pathfinder. It's a radio telescope consisting of 36 dish antennas working together as pretending to be a giant antenna. So each antenna is about 12 meter in diameter. It has a wide field of view, and the longest distance between two antennas 6 kilometers. So there's a photo there, probably not very clear because all these antennas are spread over quite a wide area. It's located in the radio quiet zone, of which Wajari Yamaji people are the traditional owner. So as you can probably guess that it has to be in the radio quiet zone because obviously it's extremely sensitive in detecting radio wave. So the project itself supports a lot of science projects listed here. I won't go through all of them, obviously. But we are supporting about more than 700 astronomers from over 200 institutions around the world. And so central to this science project is data processing. So first, the data is acquired in that using those antennas that you saw just now, and then the data is transferred to Perth, which is where the HPC POSI supercomputer is located. In that supercomputer runs a software called ASCAPsoft. This is the subject that I'm going to talk about. And then the result of this computation will be stored in the facility called CASDA. After that, it's going to be analyzed further with by astronomers to produce all the science that you will see in the publication. So this is the journey of the ASCAPsoft source code, from source code to deployment. So the blue arrow that you see there is the container. We're using the Docker container as a main facility to deploy because it's so convenient. Although I will put at my opinion on that later. So it all started from the source code in GitHub, which is internally hosted in CSIRO. We are in the middle of migration from Bitbucket to GitHub, and we're trying to simplify our process, which used to be quite all over the place, trying to centralize it into GitHub. So researchers and developers can build the Docker image from the source code in various places, including from their own laptops or VM. And it can also build from a GitLab, which is currently we're trying to also integrate the whole process into GitHub as well. We can build the Docker image there and then push it to repository, which is in the Docker Hub. And then from there, users can just pull the image, whether to laptops or PC, Mac, or what have you. And most importantly, to HPC facilities, which is, in our case, it's mostly on POSI. And when we pull the image, we pull it as singularity image because it works much better on supercomputing facility due to its way of handling permission and other stuff. So for end users, container is really great, especially if you are end user in POSI, because all you need to do is just module load, singularity, or I mean not singularity but ASCAPsoft, and in the background it will call a wrapper, which is called a container, which calls a ASCAPsoft inside it. And it's only a bit of more work if you're trying to run it on your own laptop. You don't need to build anything, just pull the Docker image to your computer, and then with a tiny bit of addition of command, you can just run ASCAPsoft. So this is really great. Compare this to the pre-container era. We used to give the entire ASCAPsoft as a source code, ask users to compile it from the source code. And ASCAPsoft has a lot of dependencies, and this is a major headache to install. So compared to that, this is a major improvement. And this is also works really great for developers because all the dependencies are contained in the container, and then you can use it for day-to-day development works. And for releases, you can also do things because it's pretty much automated as well, or scripted, should I say. And so your work has been greatly simplified using container. But although container has made our life easier in some aspects, it also has other aspects, and these are the ones that I need to discuss in this presentations. Myths about container, which we learn in the hard way. So number one is container is fully insulated, and number two, container solves all dependency problems. And number three, solve dependency problem once, and then you can live happily ever after. And number four, container simplifies my life. So let's go through that one by one. So container is fully insulated is actually just wrong, because container actually has holes. By design, it uses Linux kernel of the host system. Compare that to virtual machine, for example, because virtual machine, when you look down, it acts as a hardware. So your software inside the VM won't be able to see the actual bare metal hardware when it looks down. For the case of container, it actually see the Linux kernel that you use in the base or the host system. And it's not just Linux kernel. By necessity, because in HPC you would like to use a lot of hardware specific features to make your code run faster or massively parallel. You need to make another holes. For our case, and for many other case, we use MPI, which is a message passing interface. And the key is container inside and outside the container, the MPI type must match. So if you're using, if the Cetonix, which is the name of the POSI supercomputer, is using MPICH, then inside the container, you must use MPICH. Even worse if you use OpenMPI, because they're not compatible across versions. If you use OpenMPI 4 on the host system, inside the container, you need to precisely use version 4, not version 3. And this also goes on for other features of HPC, which is data transfer, parallel I/O. Because manufacturers, the danger here is manufacturers sometimes sacrifice compatibility for performance, and any holes that opens is a potential for conflict. And this goes to myth number 2, which is container actually solve all dependency problems. So holes in the container can really result in conflict. If you remember MPI library that I mentioned, it has its own dependency, and this dependency can be in conflict with the dependency of software inside the container. So, so if only we can put them in separate place, which luckily we found a tool that does this. It's called Spec, which is a tool that package manager specifically built for HPC environment. So the major feature about Spec is that it installs the same library or the same software by taking into account its variation. So if you install, for example, here, HDF5 library in a specific way of compiling it, you can store it in a separate place. So next time you do install another HDF5 library, it will be installed in a different place. They don't actually override each other. So this is great. And there are advantages or disadvantage of using container and spec. I just go straight to the disadvantage. This will make your technology stack even taller, which probably force you to learn more than just learning container. And myth number 3 is just if you solve the dependency problems once, then everything is good. In fact, all software and its dependencies evolve. There are updates, and some of those updates have carry breaking changes, and this will break compatibility. From our own experience, this happened when the underlying system in HPC introduced a new software stack. This include a different newer glibc library that breaks ABI compatibility with older container. So you need to be always vigilant and test things before you actually update stuff, and coordinate effort among all the stakeholders to avoid these breaking changes affecting you negatively. And the last myth is container simplifies my life, which is actually not exactly true, because you have now a tall technology stack, and it carries with it a high complexity. And so our homework now is to reduce the complexity and figure out a way to reduce apparent complexity, which is even though you have a system with high complexity, like for example, comparing modern car with antique cars, the modern car is more complex but easier to drive versus antique car, which is actually simpler but more difficult to drive. So we're trying to figure out a way to make things, even though they're complex, how to make it easy to operate. And with that, I'll thank you. And if you have, and this is just acknowledgements for all the entire teams that have been working on this project. Thank you so much for your attention.
Thank you very much, Paulus. Very interesting talk. Do we have any questions from the floor for Paulus on on this work? I guess I'll ask a question then in the meantime. In terms of your final point there about the complexity has gone up and you need to find ways to reduce that complexity. What are your thoughts on that? Do you have some directions you want to take?
Yes, so reducing complexity is actually, there are many ways of doing this. For us, the lowest hanging fruits reducing the dependency, especially those that we don't really need. You know, with complex software, a lot of times we just include things because it used to be there, just keep it there, nobody wants to touch it. But actually when you look inside, you will see things like, this code is still in Python 2, for example. Do we really need this? Can we replace it with something? Because if you replace that, suddenly your dependency trees get smaller, and it's simply easier to take care of that. Things like that. Also modernizing codes, things like some of the dependencies need to be compiled in older C++ standard, for example. If the code is modernized, then you don't have to have to compile them with various versions of C++. Just do the latest, the most modern one, and there you go, it compiles everything.
Okay, and that kind of speaks to one of the sort of debates that's been going on actually through several of the talks in terms of who do you see doing that kind of work? Is that something that you think research software engineers off to the side need to be doing in consultation with the scientists that they're supporting, or to what degree should the scientists be taking more responsibility for that?
The good thing about us in ASCAP project is that the scientists are not the scientists, but the people who wrote this code, actually they're pretty good at research software engineering. And we also have a pretty good culture in that we really talk and discuss things with each other. So, but for those who, I've been in other projects that where this is not the case, and it's always worth it to have a good discussion with researchers. On one side, to lift up their software engineering awareness and capabilities. On the other side, as for us on this side, to understand more about what is it that they're trying to achieve, because many times codes are not commented, and you do have to talk with researchers and scientists to figure out what it is that they're trying to do.
And okay, we have a question in the chat. Have you considered other container runtimes such as Podman or Saris? Once again, the zoo of tools.
Yeah. Oh, I can't wait for us to move to Podman because the bad thing about Docker is it runs as a daemon, meaning that you have to be a privileged user in order to run it. With Podman, you don't have such limitation. You can do it in the user space. But in order to do that, again, this is introducing changes, which is potentially will be breaking stuff. So I have to be very careful in doing this.
Okay. And another question I had was, so in my sphere, which is not really about productionizing or operationalizing things, but rather in data science, I talked yesterday about the issue we have in data science, where you can build a tool and you can try to encourage people to do, say, deep learning, but if it doesn't go right for them, some have a tendency to give up very quickly and walk away. And I wonder if you have similar issues around containerization, where people start to use it, then they hit a scenario where it breaks, and then they go, look, it was easier when I didn't use it, I'll go back to not using it.
Oh, yes, and it does happen. And some people still prefer to use non-container way of doing things. But with ASCAP project, we approach things from many angles as well. So we introduce a way to, not covered in this talk, we do also simplification in the way we build the entire software stack, where we use CMake as a tool. That's another tool that help us. With that, actually, it simplifies our build process, regardless whether you build it using container or on bare metal, like the conventional way of doing things.
Mm-hmm.
So, yes, I'm sad to say that to answer your question is we introduce more tools to the to the mix. But yes, some tools, as long as you do understand the limitation, is necessary. Yeah.
Okay. Yeah. Thank you very much. That's all we have time for.
Thank
But do continue in the chat, people, if you have more questions for Paulus. Thank you, Paulus. And we have the final presentation for this session, which is Chris Scott, who will be talking about virtual drug screening with AI. Thank you, Chris.
Thanks, Brent. Hopefully you can see my slides. Good. Yes, I'm Chris, a research software engineer at the University of Auckland, and I'll be talking about a project I've been involved in, virtual drug screening with AI. So this work's led by Jack Flanagan in the Department of Pharmacology at University of Auckland. We have Jack Copping and Shannon Chand who are doing a lot of the actual work here. And our involvement started as an SE consultancy project. And it's since moved across to the digital research AI team at University of Auckland. And we're providing research software engineering support. This was led by Dinny initially, and he's actually moved to the UK now. So I've taken over and providing RC support into this project. And we have collaborators in the US who are they're using and developing the AI tools that we want to use here. And like the big sort of science aim or goal here is patient-led drug discovery. What this means is that the whole discovery process is centered around the patients. So you might have patients with brain disease, you're getting samples from them. This is then feeding into a virtual screening pipeline. And out of the back of that, you're hoping to find some good candidates for new drugs. And then it's taken back to the lab and tested on the samples from these patients. So it's really focused around the patients. And in this particular sort of focused piece of work we're doing here, the aim is to achieve greater scale in an existing virtual drug screening pipeline through the use of AI. And this is what the existing pipeline sort of looks like. So at the top, you have as inputs these target protein structure, which is coming from the patient samples. And you also have these massive drug-like compound libraries that are available online. And these have billions of these small drug-like molecules that you can freely download, I think. And so with these two things at the top of the pipeline, we then need to find a way to screen through these billions of compounds and find the ones that are going to work best for the target structure. And to do this, we use tools like molecular docking, which can compute fitness scores that show how well an individual molecule might bind to the target structure. And we've got some numbers on the right there, which is say going into this docking process, we can take maybe millions, hundreds of millions of these small molecules through to the docking process. We'll filter through and maybe take through thousands of the best molecules. Will go through to the next stage, which is optimization simulation, which is more expensive, but gives you we can get a better idea of how well these molecules are going to bind to the target. And we can take maybe tens to hundreds, we can run maybe thousands through the optimization stage, and that might take weeks or months to compute. And then at the end of that, maybe you're taking tens to hundreds back to the lab for testing. So just to give an idea of the numbers that are involved with the existing pipeline that we can deal with. And there's some existing work being done with this. So this is the non-AI version, the existing pipeline, where the group have taken somewhere around 100 plus million compounds, have been screened virtually through this process, and they actually managed to find through that two really promising drug candidates. And that's really exciting work from this group. But they're always looking for ways to improve, and it's known that the more compounds you can take into the screening process, the more likely you are to get good results coming out of it. And so they're looking, instead of working with hundreds of millions of these small drug-like molecules going in, they want us to move up to billions or tens of billions. And that's where we have to look into using a slightly different approach. So this is the process with AI. It's got an extra step at the top. So we're taking those the small drug-like molecules, and they're going to feed into, and we want to be able to train a machine learning model that can predict these fitness scores that show how well these molecules will bind to the target. We still need the docking step because the docking, we need to run the docking first to come on maybe a subset of the data so that we can compute the fitness scores coming out of the docking process and then feed that into training the model. And then once we trained the model, we can just take those billions of compounds, hopefully, and run them through the trained model to screen them down to a manageable number to then go through the rest of the pipeline, like the docking and the optimization, and hopefully get better hits coming out of the virtual screening pipeline. And with this approach, we're hoping that we can move up to using millions, to running billions of compounds through this pipeline rather than millions. So this group, they've actually built up their existing pipeline over many years, maybe decades, and so that they understand really well the tools that are being used in this pipeline, how they in what situations they work well and where they don't work well. And this is really important. They don't want to switch to another wholesale to a different pipeline that uses AI. They want to take sort of a staged approach to trying to implement AI tools within their existing pipeline and see how that can help them. And some of the challenges that they're facing are mostly related to scale. So they need to download these huge compound libraries, which isn't easy by itself. And then also the docking and training tools that they're using, many of these tools might not have been used at sort of the scales they want to use them at. So going a bit more into the challenges, the first one is just downloading the compound libraries. So these libraries have billions of molecules, of small molecules in them these days. And so that they're downloading this one from Zinc 22. And the way it works, I think that there isn't an API. You have to go to the website, select which libraries you want to download, and it will give you back some curl scripts that you can download. And then you just have to run the curl scripts to pull the data down to where you want it. And it's quite long running. I think they've been running this for about 6 months now, and they've got about 70% of the way through the billion that they want to download. So they just have they're just running TMUX sessions on the login nodes and to just run these curl scripts and pull the data down. And I think they've pulled down about 4 or 5 terabytes so far. And it hasn't been smooth sailing. I think sometimes you get downtime under the service. Sometimes the curl scripts that you downloaded didn't have the correct URLs in them, so you had to go back and get new ones once it's been fixed. And you can get poor responsiveness on the remote end if there's lots of load, lots of people are downloading things there. So it takes a long time to actually pull down the molecules in the first place. So one of the key tools they're using is molecular docking. So this is the tool that it looks at the target structure, and it looks at the small molecules, and it sees how well the small molecules can bind to the target. And that's really the key way to filter out and do the screening in this process. The good thing about so they're using this gold software, and the good thing about this tool is that it's embarrassingly parallel. So if you're running 100 million compounds through the process, that's 100 million completely independent calculations. And they found that it works well to split this up into array jobs in batches of maybe 10,000 of these small molecules. And a batch of 10,000 is just, these are serial processes just running on the CPU, and they're just quite modest memory requirements, only about 2 gigabytes of memory required to go through this batch. And each batch would take of 10,000 would take about a day to run. So this uses a lot of resources actually. You know, if you want to dock 100 million compounds, that's 10,000 batches of 10,000 molecules, and 24-hour runtime gives you 240,000 core hours, which is a sizable chunk of compute time. And obviously all these 10,000 batches can run at the same time if you had enough resources. But if you, for example, if you're able to have 500 running all the time, it would take you about 3 weeks to get through this calculation. And it doesn't end there. I mean, the output of these docking programs is like a file per run. And then so you end up with 100 million files that you then need to go and collate and work through to see which molecules were best. And that can take quite a lot of time as well. So now we'll talk a bit about how we want to use AI for this initial screening step, so that we can go through billions of molecules rather than hundreds of millions. And the tool that we sort of settled on wanting to try first is AMPLE from the Atom Consortium. It's an open source modular pipeline. It's built on top of other open source tools like DeepChem and RDKit and PyTorch and scikit-learn, so well-known tools in this area. And it can be used for building models that can predict these molecular properties that we're interested in, like these fitness scores for binding the molecules to the target. Some of the nice things about AMPLE are that it's got quite a low barrier to entry, so it's quite easy to get started with. It's very high, and it's very high level. So basically, you're defining a dictionary, which you can put in settings like what type of neural net you want what type of a model you want to train, what type of featureization you want to use, how you want to split the data, and so on. So you create this dictionary, then you just pass it into the AMPLE chain model function, and it works away under the hood. So there's very little programming actually needed to be done, and very, very low barrier to entry. It has lots of features like it can do data curation. It can compute features, model training, evaluation, and it can help with hyperparameter tuning as well. And AMPLE's really built around reproducibility and standardization. They're really important features of AMPLE. So it has standard ways of splitting data. It has ways that you can compare models. So if you want to run multiple different models and see which one's best, AMPLE can help you with that. And so the way that we're working here, we're working on the NZRSE Rians platform. We decided to deploy AMPLE using Aptainer because it has quite a few dependencies. It needs specific versions of Python and PyTorch and CUDA and so on. So it was easier to containerize. We want to work in Jupyter notebooks because that's where we're comfortable working. So we have to create a custom kernel in the NZRSE platform in the Jupyter lab. So I don't know if this is useful for anyone, but actually since we moved to the on-demand system recently, Aptainer-based custom kernels don't work with the default Kubernetes backend. You have to use the Slurm backend. So you'd see when you go into on-demand, you'd see a Slurm option here. If you've asked for it, it's not there by default. So you have to ask if you want to be able to run Aptainer-based custom kernels. And so we develop and test in notebooks. And then when we're ready for production runs, so when we want to scale up to the real data sizes, we use Papermill to parameterize and run the notebooks in Slurm jobs non-interactively. And that works quite well for us because there's not much code involved. I mean, notebooks can get a bit unwieldy if you have lots of code, but there's not much code here. We just have a dictionary that defines how we want to run things and call a couple of functions. So it works quite well. So what we're doing initially is just trying to scale up AMPL and see if it actually will actually work at the scale we need to use it at. So we started small, around 100,000 molecules, and we built up to I think about 3 million so far, and we're aiming to get to about 10 million at this initial stage. We just want to profile to understand behavior, of the code. So and we're just using high-level profiling tools. So these tools don't really have any impact on the code themselves. It's just sort of OS level metrics that get reported to file every few seconds, and you can then analyze them later on. So as an example, the Slurm profiling, you can see on the right, we can get things like how many CPUs are used over time, the memory usage over time, and I/O over time. And on the left, using NZRSE, we can get things like GPU utilization over time and GPU memory. So we can get an understanding of the overall behavior. Anyway, from these initial scaling tests, the thing we found was that host memory usage was getting really big. So with 100,000 compounds, we were using about 8 gigabytes of RAM. 3 million compounds, it had gone up to 140 gigabytes of RAM. And that means if we want to get to tens or hundreds of millions, it's really going to be, it's getting too big. It's going to be maybe a terabytes of memory at that point. So we had to dig into this a bit, and because AMPL's based on DeepChem, and DeepChem has a couple of abstractions on top of the data set. The one that AMPL is using is an in-memory data set. So the whole featureized data set has to be loaded into host memory. And I think this is just the decision they made, and because at the time nobody needed to go beyond maybe 1 million or so in their training sets. It worked well for them, but for us, it's probably not going. It might not work. That there are other options though. There's also a disk data set in DeepChem which supports storing the model, the featureized data set in disk in shards, so you only ever have to load one shard at a time, and you can then train on mini batches. And that could keep the memory usage down. So we're looking into whether this might work for us as an option. Yeah, and okay, so here's just a quick showing of like when we train a model, how long it takes to train the model, and you can see that the training time is growing quickly. So for 3 million, we're up to almost a day, 20 hours of training time on one GPU. We haven't really tuned this at all at this point. This is just these initial scaling tests to see how it performs. So it's possible we could get a bit better performance. But if we switch to the disk data set, it might get worse because then we're having to load from the disk. Yeah. And here's some initial results from those scaling tests where we're going from 100,000 up to 3 million so far. And we can see that some of the metrics are getting better as we scale up the data size. And on the right, there's a graph that shows, how the predicted fitness scores coming from the machine learning model are matching towards the actual scores coming from the docking software. Okay, and where next? So we're still focusing on this initial screening stage using machine learning to compute the fitness scores. We want to continue working with AMPL to see if it will be suitable at the scale that we need to work at. There are other options. There are other tools we could use, such as PyTorch and DGL, which might have more flexibility in how we do things. So maybe we can stream data to the GPUs instead of having to load it all into memory. But it would require a lot more work to use those tools than AMPL, and we might lose some of the nice features of AMPL around the standardization and the model comparisons and so on. We're also thinking about using AI at other steps later on. There are other places where we could use AI in the pipeline. And always in the back of the mind is that, is the scale that we need to work at. You're often seeing papers, for example, coming out of the US where they're running on maybe 1,000 GPUs for a couple of days and screening through 5-10 billion molecules in that time. We just don't have the resources in New Zealand to do that. But if we can show that we can scale up on the NZ-based resources, there are collaborations like Trillium Parameter Consortium, through which we might be able to then gain access to supercomputers in the US where we could actually achieve greater scale. So that's something for us to think about as well. But that's all from me. Thank you for listening.
Thank you very much for that, Chris. Have we got any questions from the floor for Chris, please? Okay, while people are thinking, I may have missed this. You may have made this reasonably clear, but I was just wondering about the generality of AMPL in terms of the audience here. What's the scope of things that people could be using AMPL for?
Oh yeah, I think AMPL is built on top of DeepChem and RDKit, so it's very sort of chemically aware. Is if you've got molecular data, I think AMPL could probably work quite well in predicting molecular properties. Yeah, I haven't seen if it's used in other fields than that as well, though.
Okay, so you talked about the effort that would be required to move to other options such as PyTorch, DGL, and I guess there are other tools on top of that, such as MLflow. Is that effort about the retooling, or is it because essentially there's a whole lot of stuff that's domain specific and useful to you in AMPL that you would then essentially need to re-implement?
I think it's probably like the retooling. I mean, in AMPL, it's so simple that you can just run something in a few minutes. But if you want to switch to using PyTorch, I suspect you're going to have to write some more code in there. Maybe it's not like a huge effort, but it would certainly take a bit more time than what you would have to do with AMPL because it's just so simple. We almost have to write no code to use AMPL and get some models coming out.
Okay, thanks. We have a question from Nick Spencer. He's asking about, this idea that you've brought up and others have too about gaining access to overseas scale through scaling locally and then being able to use trillion parameter, for example. And he's asking, is that a strategy that for example, your organization understands? Is it an organizational level thing we should be getting into, or is it something that the researchers really have to push themselves?
Oh, good question. Yeah, I don't know if I can fully answer that, but I know it's coming from Nick Jones, who presented last week. So he's sort of the director of the group we work in. So I think it's probably coming from institutional type level rather than from the researchers, because it's coming down from Nick, who's involved in these collaborations like Trillion Parameter.
Yeah. Any more questions from anyone or comments? Okay, if there are no more questions, we'll wrap up at this point. Thank you very much to all of our speakers, and we'll now be heading into a break and returning again at 1:20. So see you all then.
Yeah, it's now 20 past by my watch. So welcome back, everybody, to the final session of our conference. We are starting it off with a Birds of the Feather session facilitated by Jana McCarr from Maker, sorry, you did just tell me that, from Women in HPC Australasia's chapter. So I'll pass it over to Jana. We unfortunately have had a cancellation of the next session, the next presentation at 2:20. So this BOF will run until 2:30, and I'll give you a 5-minute hands up, Jana. Cool. Go ahead.
Sounds great. Kia ora koutou. Thanks for tuning in today. As mentioned, ko Jana Makar toko ingoa. My name is Jana Makar, and I'm a member of the organizing committee for the Women in High Performance Computing Australasia chapter. I'm also communications manager with RIANS, and I'm based in Tamaki Makaurau, Auckland. But our chapter and our community stretches across Aotearoa, Australia, and parts of Asia. So it is an opportunity for us to speak to this group today. It's our first time to host a session in this program, but it's our second go at having a session in this sort of format. Where we're going to start with some lightning talks and then have a bit of an open, broader discussion about diversity and inclusion in the fields of research software and computational research. We piloted this approach, this type of a session at the Research Software Asia Australia conference that was ran last week, and it went really well. I also just wanted to say that I appreciated Dr. Emily Call's note near the start of her keynote this morning about women in computing. She framed it as a bit of a tangent, but it was actually a really great foreshadow for why our chapter wanted to host this type of a session. And I'll just sort of bring it up on screen here, just in case you weren't there for her live presentation. Oops. Yeah, so she'd mentioned that often it can be almost societal. Oh, yep.
You're sharing your speaking notes at the moment.
Oops. Well, that's really letting you peek behind the curtain, isn't it?
Speaking of foreshadowing.
Yeah, exactly. How about this?
Better. Yeah.
Okay. Well, now you can see what I was going to say. No, I really did appreciate Emily's call out, because she had mentioned that it's societal whims, she said, that can often either open or close a door for people in these sorts of fields. It's happened, and it still happens for women and other underrepresented groups. So that's really where our chapter comes in. Wherever there's opportunities to welcome either underrepresented people or women, and connect them with others, to appreciate and showcase their work, and give them seats at a table or voices in a Zoom call in this case. That's what our chapter aims to do. And even better if we can partner with others who are working to do the same. And I know that the Research Software Engineering Association of Australia and New Zealand do hold that as a close value of theirs. And so it's great that they accepted our BOF submission and are letting us sort of have a BOF like this today in the program. So just in case some of you haven't heard of our chapter before, I just wanted to share a quick snapshot of who is in our community. And what our chapter is all about. So you can see on the slides there that as the Australasian chapter, we've actually added a plus to our chapter name because we wanted to welcome participation from anyone beyond just gender. And also, even in a space like this, sometimes it can be domains that can be underrepresented within some of these conversations. There's lots of, technology and software and data and HPC is reaching out to touch across multiple disciplines. So making sure that they're all involved in that conversation is very important as well. In terms of who's part of our community, this is timely because we're actually in the middle of doing a community survey. So these results are hot off the presses. I just went in and checked today to get these numbers. But from our survey respondents so far, you can see that we've got a mix of career stages. 43% identify as being mid-career, 32% are early career, 14% late career, and 11% students. So that's great because, again, we want to offer a place where people can learn from each other, share experiences, and especially have early career and students learning from the experiences of those in mid and late career. We had another question that asked, do you identify as a person who's working in HPC? And you can see that 64% are definitely for sure, yes, they probably have the term HPC in their job title somewhere, so they definitely align with that. 3% were no. That's fine. Again, we're still welcoming everyone to be part of this chapter. And then 33% answered it's complicated or used the open text field to explain either why they didn't work directly in HPC or they're a fan of HPC, but they don't do technical type roles. All of these, it's really interesting what people will put in that open text field because they may either not identify with the term high performance computing or necessarily that gender term of woman, or again, don't necessarily see what they are doing as fitting in a box. So again, that's why we add that plus to our name, and we really want to make it a space where anyone can come and be part of the conversation. Again, ask what title best describes your role, and we left this as an open text field. I'm really pleased that research software engineer ended up in those top 5 ones reported there, just because, again, it shows that alignment that we do have people within our sort of chapter community that are part of this community as well, and just shows that we are working on similar things and hold similar values in terms of creating spaces for people to succeed. So I'll stop my share there and talk a bit more about the survey later, but I'll get into our session and how it will work. It's going to be split into 2 parts, and the first is that I've invited 3 lightning talk speakers to share a bit about some of the interesting projects that they're working on that either incorporate or rely on or that have been built with research software. And then we're going to move into a bit more of an open discussion with our speakers and then also you as an audience about ways we can welcome and retain and support more women and underrepresented people in fields of research software or computational research. So I've got some Kickstarter questions that I'll pose, and again, open to answers from both our panelists and the wider audience. And you can always pop in thoughts or contributions into the Zoom chat too. But so to start, we've got our 3 invited speakers. I'm going to get them to introduce themselves as part of their talk, but the order that we'll go in is Alexandra Gossart, and then Marian Tayebi, and then Mahnur Akund. And so we'll start off with Alexandra, and I'll hand over to you.
Yep. Hi everyone, I'm Alexandra Gossard. I'm a researcher at the Antarctic Research Center. I'm based in Wellington, and I will present a piece of research that I do together with my colleague at the University of Canterbury. And this research was really supported by the support at NZRSE. I've seen a few names in the audience that I recognize. I will be talking about modeling Antarctica and more specifically coupled sea ice ocean atmosphere modeling. I'm part of MB Endeavour project that looks at the future of sea ice in Antarctica. As you can see at the top of this picture, this is when sea ice is as it is normally. It has an impact and it is caused by physical and biological processes. But as you might be aware, in the recent year, there has been less and less sea ice forming in autumn and over the winter, and it can negatively impact the food chain, the biodiversity, but it can also have impact on the physical environment, such as reducing carbon uptake. So all of this is quite important and interesting. My piece in it is to try to understand all of these connections by using physical models. I don't have a picture of the models. I instead have a pretty picture of Antarctica. So basically what I do is that I run an atmosphere model, which is basically the sky in this picture. My colleague runs an ocean model, and the interface between me and her, or our study subjects, is the sea ice. And along the coast of Antarctica in winter, when the wind blows really strongly, it can move the sea ice away from the coast and open the ocean. Because the ocean is warmer, there's a lot of exchange between the atmosphere and the ocean. And these are processes that we try to represent in our big models. So what is a climate model? It's essentially a series of boxes or grid cells within which a lot of equations are solved. As you see, in the first step is to calculate the processes such as heat inputs, leaf growth, chemical reactions, etc. And then the model carries on and estimates the interaction between columns, such as the precipitation. When the precipitation occurs, it can couple with other columns or other components, and then calculates all of the physical loads, thermal energy, radiation, source losses, etc., and then calculates the motion. So that happens within each grid cell of the model. We have a region of Antarctica that we study, and it's composed by a series of grid cells in the latitudinal, longitudinal direction and vertical. So it's a big cube, let's say, and all of these processes are calculated within each of the grid cells. And that happens for every time step. So we calculate what is the state of the climate for one time step, and then we move it further in time. So this is essentially big softwares. It's thousands and thousands of lines of codes. It compiles on computers, and it's not something that me or my colleague have developed. It's big teams in the US, in Europe that spent years, dedicate years to try to represent the natural system. But what me and my colleague have done is that we have taken both of our models and made them talk to each other so that the atmosphere can send temperature information into the ocean. The ocean calculates all of its dynamics, moves the sea ice around, and then sends information about the ocean to the atmosphere. And that required quite a lot of technical developments. So we had to align compilers, we had to align flags, libraries, and make the model run and exchange the variables and the information we wanted them to on HPC. And we did that, the two of us, but then with heavy support from NZRSE. So this is represented in this graphic here. We have the ocean, the sea ice, the atmosphere, and they all talk to each other through a coupler, and we end up with stacks of cubes that exchange and interface with each other. This is text I've stolen from someone demystifying climate models, a publication, to maybe help explain that we need a lot of resources. So the cost of running those climate models really depends on the size of the domain. In my case, I have 200 grid cells in the X direction, 240 in the Y direction, and 61 levels. And that's for the atmosphere only. The ocean has similar values, but that's more than 3 million grid cells for only a small part of Antarctica for one time steps. And then everything has to be calculated further in time. So the speed of the calculation is not as important as the number of core, because we do a lot of calculation in parallel. So it's not really the time, but the number of cores that we get that will make the runtime shorter. And one big component of our model is that we need to communicate between the columns. So we can only use specific computer hardware. So we are very reliant on HPCs. It's not a type of model that I can run on my laptop. And I believe that's all I have for today. Happy to take questions.
Yeah, we do have time for questions if any of the audience wants to dive a bit deeper. I was saying, I know we have only given these fantastic speakers only a small, like 5 minutes is difficult to scrunch everything into. But if you do have a question that you'd like to ask, please feel free. You can either unmute or type it into the Zoom chat here. I have one question quick that might, if anyone else is preparing what they would like to ask, but I guess, how do you see the sophistication of these coupled models maybe changing in the next, 5 to 10 years? There's probably been a lot of change compared to when you started, or or how do you see
Yes,
it changing further?
definitely. I think machine learning and AI will make big changes because, as I said, it requires a lot of computing power. Those models take a lot of time to run, and wherever shortcuts can be taken, I think they will in the future. It started with very simple models, and that, you know, in the 70s, and then as time goes by, they get more and more complex, but also more heavy and difficult to run on such platforms. Yeah.
All right. Did anyone else have any questions that they'd like to pose? All right, we do have a question in the chat. It says, what programming language are those two models written in?
Yes, I didn't mention this. They're written in Fortran.
Great, another callback to Emily's keynote talk this morning. Fortran reigns on. All right. Well, just in for the sake of time, we're going to now move into a field of medical sciences. Again, one of the goals of this session was to bring projects from different domains. And it's interesting, the session that I ran last week, we had this beautiful overlapping, actually, of similar domains. All my speakers had connections either through institution or their fields of science. But this time we do have a bit more disparity across the ones we're featuring. So over to Miriam.
Thank you so much. I hope that you can see my screen. Yeah, great. Thank you so much. Thank you so much for inviting me for this talk and having this lightning talk. I tried to be 5 minutes, but I might not be able to achieve it. So my talk is going to be the application of the HPC in our research at what we're doing in our research team. So I wanted to start with a little bit about my journey to talk about my background. So I started my study from Iran when I started my bachelor in radiology. So I studied there and then worked at the hospital for a couple of years as a radiographer. I've worked with the different imaging machines from CT scan, radiography, and MRI. And then I decided I want to continue with my education. So that's why I went to the UK and studied master in medical imaging, where I become more and more familiar and introduced to the physics and programming and engineering a little bit. And that's become a kind of an introduction for me to be able to shift my interest toward more research. So I started after that working as an imaging scientist and researcher in that area. And then I wanted to continue my education. So that's how I found the PhD scholarship at Auckland University. And I joined the Bioengineering Institute at Auckland University. And then I worked there and finished my PhD. And then now at Matai, I'm working as a neuroimaging scientist in my research fellow job. So the big goal for our projects that we're doing here at Matai is to using the different MRI technique that acquiring different imaging modalities and then extracting different biomarkers from them to be able to help us to especially help clinicians for the diagnosis, prediction, or treatment. And that's the main focus for my project, is focusing on the different brain health conditions. So during my PhD project, I was working and focusing on the mild traumatic brain injury, where we were trying to help improving the diagnostic for the methods that help clinician, and especially we were focusing on the sports concussion, like we were working on the rugby players to help them to be able to detect and diagnose concussion as early as possible. And in my current research fellow job, I'm helping and more involved and leading the project and the investigating the brain recovery during the methamphetamine addiction, when people stopped taking meth and they started their abstinence journey. So both of these projects, as you can see, they're related to different brain health conditions, and we're mainly focusing on using the MRI images for our research purpose. So just a little bit of a summary. So in clinical practice and the traditional methods is usually the qualitative way of radiologists acquiring the images and reviewing them to detect any abnormalities. But in a more advanced techniques in the research, we're acquiring more data and information from different techniques to be able to provide more quantitative analysis. And that's what we're doing in our research team. So we're acquiring so many different techniques of MRI to be able to see from the structure, the volume, the function, and different aspects of the brain to help us to detect any abnormalities or help for diagnosis or detection of different disease. And each of these methods we can acquire so many different parameters, like I just put a few of examples there. And that led us to kind of dealing with so much data in our analysis. So during my PhD, I become more familiar with different imaging software that I had to choose and use for my analysis. And it was quite a tough time for me to be able to familiar myself with different of them, because each of them written in different language, had their own style of like programming and stuff. So it was kind of a bit of a steep learning curve for me. But eventually, I was able to learn and then running most of my analysis on the HPC provided by Auckland Bioengineering Institute, and lots of our data was saved and stored on the e-research platform. But toward the end of my PhD and beginning of my research fellow job, I became more one of my colleagues introduced me to the NZRSE platform. So like knowing NZRSE and working and collaborating with their team help us to for our analysis to be more structured and more well organized. So with the help of NZRSE team, and I can see some of them online here as well, we were able to move and shift our analysis to the SnakeMake workflow system. So it's kind of helped us to provide all different analysis parts that we had in our analysis to be able to make it more structured and very more well-organized system to help us for lots of the different analysis that we needed to run in our study. So there are some parts that was fun during working in these research platform areas. So working and automation definitely was one fun part of it, because it definitely increased the reproducibility, especially in our research area. It reduced redundancy and the productivity was higher. And then we were able to run more faster analysis, and the version control was easier as well. And I was able to share the pipeline that I made with the help of NZRSE team with other students and collaborators, which made this, again, help for the reproducibility. And definitely there are some challenging parts where, especially for me that coming from non-engineering or programming background, this steep learning curve was definitely one of the most challenging part for me. And debugging, which I've never really experienced, but it seemed like the nature of the software and programming part. So it was the pain at the beginning, but I realized help and solving them is kind of fun. And definitely always the limitation in the resources in terms of storage or CPU and GPU is always part of it, and making adaptability and making adaptable with the new updates and configuration is always one of the challenging that is with us. I'm personally proud of all these learning and contribution that I had toward reading and learning about these all the analysis techniques and software. I don't call myself software engineer, but just learning about how the software engineering works and providing it as a pipeline for my research. And these pipelines now can be used and improved by my students and other collaborators as well, which at the end helped the whole team in our lab to kind of produce more and be able to share better results in a shorter amount of time and with a higher production and their publications. So at the end, I wanted just to celebrate these opportunity that I had, I think, with the celebrating people, but empowering diversity and strengthening research, we all can contribute to a better science. Thank you so much.
Wonderful. Thank you, Miriam.
Thank
Does
you.
anyone have any questions for Miriam? Again, with that whirlwind tour of a project that I'm sure you could speak for hours on.
Thank you.
One question, I guess, did you see yourself having the skills today that you've acquired through these projects? You know, thinking back 5 years when you began your journey, I like to showing the progression there.
Yeah, definitely not. I mean, funny enough, because before I actually started my medical as my bachelor, I always loved to kind of was fascinated by the engineering groups and people who were going toward that way. But I always had this mindset that, oh, engineering is not much for women. It's just kind of always feeling like, oh, medical area is more women friendlier. But it's kind of keeping in my mind that one part of my future might be engaged with engineering. And I'm glad that it actually happened. And I started like my PhD in the Engineering Institute. It's kind of helped me to recognize that it's not just a scary area that you just male need to dominate it. So it's kind of helped me to become, I had a supervisor, were all women. So it's kind of made me a bit more relaxed to getting involved and then opening the doors for me.
Ooh, wonderful. And we've got a question from Emily in the chat. If you could wave a magic wand and change one thing on the HPC services to make your workflows easier, what would you do?
And the workflow, definitely. I mean, as I said, we had a massive, great thanks from the team, from the NZRSE team, because every time that we got stuck, so they were able to help us and like give us some hints and tricks and like what to do and how to continue. But I would say probably from the kind of a guideline point of view, if it was a bit more diversity of the information in terms of like anybody with different level of knowledge and background can grasp these knowledge and be able to apply, that might be something that I would appreciate if they would existed. But I always see it from my point of view that because I'm not from this community, I need to learn more. I never really thought that would have been nice if they thought about people with my level of knowledge as well. But yeah, I think that would have been something that I would improve. Yeah, exactly. Documentation and training. Yeah.
Yeah, that's a great point, especially, you know, if we are seeing HPC and software and, you know, these types of approaches being adopted across different domains, and we want to enable that, then how do we, open that door and let people acquire the skills needed to do it?
Yeah,
right.
Exactly.
All right, well, this is a great segue as well in terms of having across our lightning speakers, people from different domains and different perspectives. And I'm really pleased to welcome Mahnur to join us because she is at more of the beginning of her career journey. I found her through asking around at the University of Waikato, and she's a master's student who recently completed her thesis and is now doing some teaching and research work. And so I hope, you know, very keen to hear sort of the things that you're working on, and then and share that experience of you in your early stage of your research career. So over to you, Mahnur.
Thank you, Jana, and hello, everyone. I'm Mahnur, and like Jana mentioned, I'm very early in my career. I just graduated, and currently I'm teaching and doing a bit of researching at my university. So I'm excited to share a part of my research in the area of applied AI in smart agriculture. So applied AI in smart agriculture is actually a really vague thing to say. So let me give you a little bit more context by starting off with like the problem in kind of like a nutshell. So there are farms, and there are a lot of them, especially if you're living in New Zealand, and they are generating a lot of data, but these farms, they are typically in rural areas, and they often have like terrible internet, and also a lot of the data that's collected, the farmers consider that sort of data a valuable information to them. So for them, it's a private information, and it's something that cannot leave their farm and go to something like a cloud or a central server for processing. So a popular solution that exists is something called federated learning. This is like a form of machine learning, and it kind of falls under the domain of distributed learning. And this is like an idea where instead of sending data to a centralized server to train, let's say, like a global model, instead training is happening locally, and you have the model parameters being sent for aggregation outside of the farm to some sort of a server. So in these kind of scenarios where federated learning is being adopted, what's happening is that local training, it's happening on the devices in the farms. So the data stays local and private. So sounds like a perfect solution. What's the catch? Well, the thing is, the current literature on federated learning in agriculture, although it's new, but it's like rapidly growing. Most of the research is kind of happening in kind of like a perfect, clean simulations. And for a good number of years, the focus has been on improving algorithms rather than focusing on moving forward with what we already have in terms of the algorithms and consider the real world messiness of the farm. Because the end goal of the algorithm is to get deployed eventually in the farm. So the focus also as a research community needs to shift a bit. And this problem creates what we call a reality gap. So we have very little idea, and there's also a lack of substantial proof that all these federated learning algorithms that are working perfectly, may I say, in labs and simulations, but we don't even know if they will actually function on the farm. So that's a bit of context, and that is where my work comes in. And my work was done in collaboration with the Rural AI team. So this is like an international team that is dedicated to bringing, as the name suggests, bringing AI to rural areas, to rural communities. And agriculture in rural areas is something that they are working on. And my role was to kind of drag this research out of this theoretical realm, this theoretical world, and bring it a tiny bit closer to reality so that we can move closer to the deployment stage of these algorithms in actual fields. So what did I do? Well, I will move to the next slide. So I designed and built a reproducible hardware-based testbed. So that's kind of what it looks like. So what it basically is, it's kind of like a system of small, low-power devices, just like anything that you'd find in actual farm equipment. And my main contribution was building this entire system from scratch, so like from ground up, and documenting it well enough so that it can kind of be reproducible and set a standard for us to see if an algorithm that's working perfectly in simulation, if it can actually work in the real hardware or not. So I didn't just build like the system. Of course, I picked one of the state-of-the-art federated learning algorithm and I tested it in this architecture, and I tested it in simulation, and I compared whether there is something there. And my results showed that, as expected, the reality gap does exist. It was something real. It was not something in our heads, and it was pretty huge. So out of several things that we did quantify, I will just mention one of them that we did expect and our results did show, which was that the AI training time in simulation took 17 minutes. But it took approximately, if you approximate this, it took 2 hours on the real world hardware. And we saw this massive slowdown across all our tests that we did. So what this means is that the software is only as good as the hardware it runs on. And it needs to include, we need to include the hardware in our loop and benchmark the system metrics when we're testing it. So this brings me to what you could say I'm most proud of, which is that we are making this entire system, so all the code, all the configuration, fully open source soon. So also note that I would like to make a mention of this. It's not that the researchers are not testing their algorithms on hardware, and it's not that they're not quantifying its system metrics, but a lot of them either have setups that are difficult to reproduce, or they're measuring metrics for the same use case that are different from others. So it's very hard to compare which federated algorithm is working best on a particular hardware for a particular scenario, for a particular use case. So in my case, I was focusing on smart agriculture. So by creating this sort of tool that other researchers can easily replicate and collect results in kind of like a standard way, we can now compare our results, and hopefully we can like take this promise of federated learning in smart agriculture out of our simulations, and we can move like a teeny bit step closer to make this work in the reality of the field. So this was a small part of my research that I had. Thank you.
Wonderful. Thank you so much, Manur. That was really interesting. I really like that term of the reality gap. And that probably is something that could apply to a couple of different domains as well, in terms of, yeah, what you're working on may work great in a simulation or in the lab, but once you get into the messiness of a farm to see if it actually does work, that's the test.
Yeah, one thing that was very interesting in the literature was, like, I appreciate the fact, and I'm not against that, we need to improve current existing algorithms, but the focus is that eventually these need to be deployed. So we need to kind of shift the focus in how we are approaching this segment of research.
And did you find even that there is, I guess, diverse types of hardware and scenarios even across the farms across New Zealand? Like some may be better positioned and early adopters of different technology and approaches and hardware amongst themselves even?
Yeah, so currently from our survey, we have found out that farms, they are using hardware, but they're using very low-end hardware. So I didn't exactly emulate a certain farm's hardware device. Instead, what I did was I picked a available low power, cost-effective hardware, which were the Jetson Nanos. They were readily available to me. They're not particularly cost-effective, but that was what was available to me. But the idea is that the configurations of these Jetson Nanos can be translated to other hardware devices that are used in farms like Raspberry Pi maybe as well.
Cool. And we have a question in the chat. Can you give a bit more details about the hardware of those modules?
Yeah, so the hardware that I used was Jetson Nanos. In the communication, that's okay, to give more detail about the federated learning that we tested, it was a flight, which is considered in their paper as a state-of-the-art federated learning algorithms. And we deployed that on Jetson Nanos. We deployed it on six Jetson Nanos, and they are communicating through the internet to the cloud. So I hope that's enough detail about the hardware of these modules.
Great. All right. Well, thank you all for, again, these are just short glimpses of some of the really interesting work that's happening out there. And I'm keen to sort of dive a bit more into raising the conversation up a little more. We're going to talk a bit more about the sector, about the different ways that we can, encourage and retain more people to participate in research software and in computational research, so that we can continue to have impacts across the range of domains and have different perspectives and people who, no matter what their journey may be, I like that, Miriam, of your journey was up and down and up and down. I think we know that someone's path within research is never quite linear of A to B. But yeah, how can we make sure that we don't necessarily lose people along the way? And how can we encourage more people to stay and to excel in this space? And so one of my Kickstarter for discussion questions that I wanted to pose to the panelists, but then also open up to the audience if they wanted to chip in as well, is, I guess, along your way and your experiences so far, have you encountered any barriers or challenges? And by challenges, I don't necessarily mean the debugging one, but more of in terms of challenges to feeling like either you or your work maybe wasn't accepted or necessarily welcomed within the field, whether it was being a minority within your graduating class, or maybe your new ideas weren't necessarily accepted within a research group, but then you went off and found one where you could find collaborators, or anything like that. Are there any examples of sort of challenges or barriers that you encountered along the way? Or if not, it's great to shout that out too. And if you've had people support you and champion you along the way, we definitely want to hear about that as well.
I can just briefly talk about my experience because I think I briefly mentioned it in my presentation. Because of my background, so it was quite a new area for me to kind of adapt myself with all the new learnings. But I found that, first of all, the environment that you are at and then how supportive people can be, like that really affects that, like you don't feel like you're getting overwhelmed with the amount of knowledge and like learnings that you have to get. But at the same time, it's kind of a bit of like, I don't know what call it, imposter syndrome, that you feel like you're not good enough, or what you contribute is not like valuable enough to be able to share it with a bigger audience. But one thing that happened, like at the beginning of my PhD, that's what I kind of experienced. But toward the end, and then getting to working and collaborating with the software engineers from NZRSE team, I realized that like whatever I make is also can be packaged and framed in a way that can be used by others, and it's nothing less than what like other people or other groups do. So it's kind of slightly changed and shifted my perspective, because it was kind of, I always thought it's such a high level expectation, people like I can't really reach that level. But it kind of gave me the idea that it is doable, and especially like every little thing that you do for your unique and like novel projects that you do is kind of valuable enough. So it's kind of, yeah, shifting this perspective, and then supportive community, it helps, definitely.
Yeah, that's a great example of each person. Yeah, their value and their competition or contribution has weight on its own, and necessarily some of these big, especially these big collaborative projects that we all work on, if you don't have certain participation, then it wouldn't be the same project, right? And so each person does have value in their role. Alexandra or Manur, did you have anything that you wanted to share on that note?
Yes, I guess a bit similar to Mariam. I never thought I would be doing what I do now, and I never really studied IT stuff. And I fell into it, and I had to learn and understand quite a bit by myself. But I've always found, even during my PhD, when I started with using those climate model, and then here during my postdoc, a lot of support from HPC research engineers, and they always manage to translate the things to me in a way that I understand. And I try to do the same with what I do. And I think keeping the communication open is very important. I was also very lucky that I think those people are genuinely interested in what I do, and not in terms of the software, but also the results and like the final aim of the research. And then, yeah, exchanging with them, I feel a bit less stupid or annoying, knowing that they see a use for what I do. But I think that technical jargon and this big idea of IT, HPC, can sometimes be a barrier to someone who just starts doing research and doesn't really know much. Yeah.
Yeah, I really like that, and that mention of imposter syndrome, because we definitely see it in a lot of different fields, and it's these terminologies and these titles, and you know, if you don't feel like you fit or stack up to that, everyone else might think you do, but if you don't, then it can prevent you, I guess, from feeling like you belong. That's definitely something that we've seen in some of the activities and meetups and discussions that we've had as a chapter. And Mahnur, I know that you had even mentioned like, oh, I'm quite early in my career, and you know, is
Yes. So although I'm quite early in my career, I kind of really agree with Alexandra, that there are some jargons being used here and there, and I have a certain vision on how the research should go. But since research are not done alone, you have to do it in collaboration with others. So you have to take into account what their vision is, and then kind of reach like the middle ground, a compromise, and then work towards that direction.
Yeah, I like that. I really like that. We've got a compliment from Alex in the chat, and he'd mentioned that Emily mentioned that computing is at the service of science, and so every research area is more interesting than computing on its own, in Alex's opinion. But he does say kudos to all of you scientists. I agree. And then, yeah, I think the only people who don't have imposter syndrome are cats. They own that space, and they are happy to be wherever they choose to be at that moment. So another question then that I might want to pose is again, one of the motivations that we had for hosting a session like this is to, invite people that I saw were not on the program already, bring them into the fold and ask them to give a 5-minute lightning talk. But how do you see maybe us taking efforts like that to give visibility to more of the different types of work that is happening out there, the different types of people who are interacting with research software and benefiting from research software and learning skills? How could we do more to highlight those efforts and things happening in the long term, not just one session today and these 3 lightning talks, but how can we continue to make sure that there's recognition and career opportunities and collaboration in this space? Do you have any thoughts?
One idea that I had was like what I noticed that when we were preparing our CVs for like different grants, application stuff, we always have sections for like, what are your conferences, what are your papers, but there's not much area of like, what is your contribution in that? Like, I mean, for different groups are different, but at least for the people who are working in that area in terms of like contribution in making some research software or something like that. So I think that's the kind of a missing part, because I guess like everybody here agreed on that this part of making some software or making some pipeline that eventually lots of the research program output rely on is quite a time-consuming part. And people who contributing in that part definitely needs to be appreciated, not just necessarily like somewhere their names in the like papers, something a bit more like clear and more like dominant. So at least putting it somewhere, like become kind of a routine to put it in somewhere in the CV or allocate some space for it, or in the grant application, that probably would help quite a lot. And also in like, for example, when you do the like institutional promotions and evaluation, just kind of your contribution in that area. I don't know about different groups, but I know that in the medical area, it's kind of research software is not quite a clear like location position wise. So it's kind of your contribution might not be appreciated as much. So that's something that kind of can be thought and be talked about with different groups and research groups as well.
Do you see that, has that changed over the last 3 to 5 years? I'm trying to, how long, Janet, how long has the Research Software Engineering Association in New Zealand and Australia been around? I can't remember. Is it 5 years? Longer?
Something like that. 6 years, something like that. I can't remember.
Yeah.
I can't remember when I started.
Oh, 2018-ish, Mary's saying, yeah, I mean, that recognition and that, and as you say, of different contributions is definitely something that hopefully is happening more. But I guess it needs also that buy-in and support from within our organizations and then above us as well, and leaders too.
Exactly. Yeah.
Totally agree with that point. And if anyone has any ideas of how we can drive that recognition of software as being an output of research, then please reach out to RSE or Women in HPC, anyone, to suggest things, because it is a real struggle to try and get stuff. Yeah, if anyone wants to see a cat in person.
Has anyone seen, I guess, any efforts, community practices or initiatives that are helping with that visibility and or that recognition elsewhere, either locally, say within your groups, or globally? Oh yeah, Emily.
Yeah, so within Australia, at least, the Australian Research Data Commons has been doing a lot of fantastic work at raising the profile of research software engineers. And like 2 of the really big things that they've done in this, actually, I suppose 3, we're getting out of hand here, but 3. One is just like having extra ways for like creating persistent identifiers for software projects. So making it easier to go from a code repository to a DOI that you can then cite places without having to go through a formal publication metric, but it'll still track things like, citation counts and that sort of thing. But also some really useful stuff has been like creating the Eureka Prize for research software. So like an actual prestigious award that's like, here is useful research software. It's, you know, it's a big black tie event, all of that kind of stuff. And then on a smaller scale, doing just like monthly profiles of research software engineers on their website, where they interview people and say, hey, what are you working on? What do you think's cool? That sort of stuff, just to try and get that exposure out there to the broader stuff. So like, if folks are in a position in New Zealand to do something similar, that's something that's been quite useful within Australia at least.
Mathnor, I'm keen to hear from you. Like, what was your graduating class like in terms of people from different backgrounds and or entryways into your field? Was it diverse or?
As in entry field into the academia?
Yeah.
And
even
from
your
my
research thing.
graduating class, I'm the only one here. So there's not much opportunities for like early careers to get like permanent roles in academia. So it makes the field of research or like working in academia a bit unstable, and like we want to go with stability most of the time. So a lot of the graduating cohort, they're now in the industry as opposed to academia. And also I've seen good efforts by the AI Institute here, where they, part of, I think, a bigger group, they organize hackathon. I think at certain periods of the year, 2 or 3 times, where like students, not just students, but researchers, early careers or PhD students, where they get to whatever they're working on presented to a group of audience that are part of the industry and get like good feedback from there. And I think that's pretty useful to know that if the research that we're doing is actually applicable to the industry as well, because at the end of the day, I mean, we're doing research, yes, for the sake of innovation, but also to eventually impact businesses in some way. So I feel like it's a good collaboration between academia and industry by organizing hackathons, especially in universities.
I noticed your research project too had quite a few collaborators, global ones as well. There was some in the US and Australia.
Yes, it was an international team, so we would have bi-weekly meetings. So we'd have researchers from the US, the UK, Australia, and of course New Zealand as well. And also collaboration internationally is very difficult as well, because again, as a researcher, everyone thinks differently. We have different visions and goals. So coming together and agreeing on one thing and moving forward in that direction takes a bit of effort, and sometimes research can be slow for this reason as well and a bit fragmented.
Alexandra, do you find that, I mean, I'm sure a lot of the work you're doing with your the climate modeling is tapping into international collaborations and groups there as well. Yeah, do you find that there's some challenges often in getting, yeah, collaborations across the board and people participating and contributing?
I think in our case, we are more end users of the code, so we stay up to date with the model updates. I think it's a bit maybe difficult to get them to take our coupled model on board. It's a bit complicated because there's big institutes and each institute has their own model and they love their baby and they just do everything with that one. And basically what we've developed here in New Zealand will, if we stay realistic, probably only ever get used here. So the challenge would be to recruit PhD students and just keep the capability here within New Zealand. And that's also a challenge, I would say. There's not that many PhD candidates which have the required skills or the envy to pursue a PhD in this field.
Do you find that, I guess for my 3 lightning talk speakers, you know, you've acquired these skills and knowledge in this space through your work. Do you see that there's more opportunities to do that for incoming people, people new to and beginning their research journeys, more than maybe what was available to you? And or how do you know where to go next in terms of what skills to develop and how to get yourself ready for where things will go next?
So one thing that I have the experience with is at Matai, we are doing summer internship for undergrad students. So that's the opportunity that we're providing for people who are living in that region, like in the Gisborne area in east of New Zealand, and to make them familiar with the research environment, as well as some skills that they need to kind of prepare them for if they're keen to go for postgrad. And as one of the training that we're providing is to familiarizing them with the basic level of programming, coding, especially because kids or these undergrads coming from quite a different type of background. There are engineers, but there are lots of health science and like a medical science. And what I personally experience is that they become more familiar with these concepts. They know what opportunities in future they will have, and there's kind of not kind of a closing their mind that, oh, there's just a couple of options that they have to go. We kind of trying to show them the diversity of options that they can shift and move toward their future career or study pathways. And because I was teaching a couple of these courses, and then I experienced that even some of these medical students, because we are kind of combining these programming languages with what in the medical analysis they can use, they kind of started becoming more interested in the area that they never really heard even during their university studies. And after they went back to uni, they actually were able to show what they learned to their like instructors and to the peers. And it was kind of for me to see that like there are some skills that the undergrad, even if they're not directly connected to the software area or programming area, if they learn, it can be very open-minding for them in future. So that was a kind of a live and my own experience that I had with the undergrad level.
Great. And I think too that that's a good mention as well of again another opportunity of opening a door. Geographic location and rural connectivity and access to some of these opportunities can really be beneficial if you can take it to
exactly.
All right, I might do one last call for questions about anything, either related to this broader topic about you know, increasing diversity within our workforce and within the sector, or if there was any other last questions that you had about each of our speakers' lightning talk. Please feel free to pose now, either in the Zoom chat, and I'll share one last closing slide. Because I did want to put in a pitch to have everyone participate in our Women in HPC chapter survey, just because, again, we can learn a lot from this community, and I think we do have overlapping values and things that we're passionate about in terms of wanting to encourage representation and celebrate those who are doing interesting work in this space. So I've got a QR code there, but if you would like to participate in our survey, that should link to it, and I'll also put the link in the chat. I can bring up my chat. But we do welcome your contributions, and we're aiming to close the survey on September 30th, and then we are going to share the results at the eResearch Australasia conference and also across our channels. And then one last plug is that if you would like to join our chapter, and participate, we definitely welcome you. We have fortnightly Zoom chats where they're just casual hangouts where people can come and meet others in the chapter, again, across the region of Australia and New Zealand. We also have a very active Slack space. We have a newsletter. We have a LinkedIn presence too. But I think the Slack and the fortnightly meetups are probably our most active places where we can continue conversations about some of this stuff and be sounding boards if people are looking for advice, or again, just looking to meet other people working in the same fields. Or sometimes our fortnightly chat up meetups have people just getting into some technical details and hashing out some problems that they might be struggling with their workflows or their code or that sort of thing. So definitely welcome everyone to join and be a part. And I'll stop sharing there. And thank you again for this opportunity, and really appreciate the audience in listening and welcoming our three speakers. And I hope that they're able to make some connections if they don't have already with the rest of you in this community, maybe after the conference. But yeah, I've found that the RSE community here in Aotearoa is very welcoming and supportive, and so definitely encourage people to tap into those resources and the people that are part of it, because yeah, it's a great community to be a part of. So thanks very much, Janet, and I'll hand over to you.
We have a little bit of time for questions as the next presentation was unfortunately cancelled. So our next presentation will be starting at 2:40. So if anyone's got any questions for any of these speakers, and I'll start by saying thank you to all of you. It was really cool to hear the work that you've been doing. And I think you should consider yourselves to be RSEs, because in my mind, an RSE incorporates anyone, whether you're from a domain or not from a domain, working with research software or research code to do something amazing. So I think you can all consider yourselves to be RSEs. And I'm very interested in the work that you did with the rural AI, because in forensics, crime scenes don't just happen in cities, they can also happen out where there's no connectivity. So in order to get some of the cool tools that are coming on board out into the hands of the people doing the hands-on collection of samples is something that is definitely topical for my field, at least.
In that case, I'll keep you updated on the progress that I'm making on this research.
That would be amazing. Has anyone got any other questions or comments? If not, we'll take a short bio break and come back for 2:40. Make sure I've got that right, for Jorge. So everyone just hang tight. If you want to chat, then go ahead. Otherwise, thank you again very much to our speakers here, and it was a really good session.
Cool. Thanks so much.
Thank you.
Thank you.
Okie dokie. We're on the home stretch for this last session. And I would like to introduce our next speaker, Jorge Borman, who is a HPC research software engineer from ESNZ, who will be speaking. I've lost the page. Oh, there we go. On CSET, a powerful, flexible, process-orientated evaluation toolkit for convective and turbulent scale weather and climate models. That's a bit of a mouthful. Share at your convenience, Jorge, and
Can you see the?
Perfect.
Yep. Tēnā koutou katoa, ko Jorge Bornemanto ko ingoa, he kaimatai rorohiko ahau ki Earth Sciences New Zealand, and I'm going to present CSET, our new evaluation toolkit for high-resolution weather and climate models, on behalf of the development team, which both here in New Zealand and also at the UK Met Office. The outline of the presentation is just motivation behind this new tool, going through the design, the implementation, so a few nice pictures, and then where are we going from here? So the Momentum Partnership is an international conglomerate, an international cooperation for of 10 weather and climate centers, and it has as one of its priority areas a technical infrastructure development to support the science behind. And is this technical infrastructure program together with the Met Office, the UK Met Office that funded the CSET development. So part of the for the science that we deliver needs a joint science program, and that one of the key points of that is a common evaluation tool. The previous tool we had serious portability issues, so we ran a quick survey of the toolbox. I found a picture similar to the one that is depicted in the slide. It's not a criticism of what was before, it's much more a reflection of how the the thinking on research software has changed in recent years. So going through the design, first start with a few concepts. Fields, and I know that the name is not adequate, we have been agonizing for 3 years over this. Is basically data. Multidimensional arrays of gridded data. We have targeted it to the meteorological variables because it's our science, but it can be any kind of gridded data. The analogous, if you're familiar with XArray, will be data arrays. If you're familiar with the IRIS framework, is cubes. Then operators. An operator is basically a simple transformation on several fields, and it can be a simple unit conversion, just only changing values, but can be also meaning over one variable, in which it changes meaning on one dimension, in which change the dimensions, or it can be subsetting, change size, anything, but it's basically, it has to be very restricted and simple so we can move the pieces around. And moving the pieces around and chaining them together using a set of instructions that we call a recipe. We create a diagnostic, which is when we have an input file, apply a recipe, and get the results. So to move the operators around and use it in different parts, in different orders, when we are running different recipes, we need the same data structure of field as input and as output, regardless of maybe different dimensions, etc. And the only exception to that is that in the load operator that gets the data, the input is a file, and the plot operators that the output are graphics files. So another thing to consider in the design is that we have a very wide and varied user community. So for that, we designed, or we thought of users scenarios and role-played their interactions with CSET. So for example, in this case, a researcher that develops a new diagnostic coding a recipe must have the capacity to edit a configuration file, must be familiar with the API with the operators, but doesn't need to know how the operators are built inside, how they manage the dimensions, and all the nitty-gritty, how to parallelize So we isolate the user from that part, just going towards higher these others. We even isolate the users more from the code. Going into implementation, it's mostly written on Python with traces of some other languages. And then the engine, the core of CSET is based on Iris, which is a tool similar to Xarray, but it's as we were dealing with data from the Momentum partnership, is more tailored to that kind of data, but also understands perfectly fine NetCDF files. Interacts well with Matplotlib to generate plots. And for the code management point of view, we have used GitHubs. The recipes is basically a YAML file format that specifies the different steps to build the diagnostics. So going in a bit more detail, imagine a very simple case in which what we want is to plot a postage stamp of a forecast, an ensemble of forecasts. We get as input our file, apply one operator that loads and selects the variable that we want, in this case temperature, and selects the level, in this case 1.5 meters, gives us our field, and we apply our spatial plot operator on that file that gives us our postage stamp plot. Now, if instead of this postage stamp, we want an ensemble mean, we just insert a collapse operator, basically an operator that takes the mean over the realization dimension, the realization coordinate, between the constraint and the spatial plot. And that in CSET is achieved with just only 3 lines in the configuration file, in the YAML file, defining the recipe, as is specified here, highlighted in yellow. So from the user point of view, it's super flexible and super easy to interact with. That works well. It's good for to create a single recipe. CSET has a command line interface that makes that very easy. But to get all the power of that, if we want to scale up, run many recipes, many days of forecast, for that we use Silk. So, and Silk will give us a workflow. We could create a Silk workflow with CSET in the middle. Silk not only runs CSET in parallel, but also organizes the files before, creates an output web page afterwards. And as CSET is creating the plots, it also generates metadata that appends to a JSON file, and that is used to create the web page index, which is shown in here. And in the metadata, we specify the diagnostic group, forecast group, and the diagnostics that are shown in the left part of the web page. And also in the entry part, in the entry page, we have a link to how that particular CSET workflow was run, and that gives us the provenance and the repeatability of the experiment. In terms of objective verification, because CSET is mostly process based, but we still want to run the statistics. We are basing that on MedMed Plus, which is a very well used verification, objective verification library developed in the US by the Development Test Center. MET is written on C++. It's a very powerful verification toolset. And MET Plus is a series of Python wrappers that provide an interface layer with MET tools. These MET Plus wrappers, are we going to code them in the CSET workflow? It's important to notice that the CSET workflow is not, so the CSET is not, MET is not going to be part of CSET, but is going to be part of the CSET workflow. And it uses, the implementation makes use of very nice MET capabilities to make things easy, particularly dealing with things fiddly as local observations. And to produce the verification plots, we are going to use another Momentum toolset. So going now into nice pictures, the web page that you have seen before on the left panel with the indexes, it can provide side-by-side plots to compare, but also can provide single plots if you want to see things in more detail. And whether it is side-by-side or single plots, you can have a description if you want, and you can add a description of the diagnostic that is provided with the metadata. And if the plot requires that, you also have a scrolling bar at the top that can navigate you and animate quickly through your results. At the CSET library at the moment has 52 recipes and growing. And it's important to note these two, the age of the air and elevated convection, because those have been created specifically with CSET. So this there was nothing before that has been translated to CSET that has been used, created using CSET alone. In terms of next steps, we want to introduce observations, and the Met Office team is working quite hard on that at this moment. We have been working with our climate scientists to start creating climate diagnostics. This has some interesting challenges as finding data sets with trillions of data points. And also creating new operators to partition the time dimensions in different way. We want to expand to global numerical weather prediction data sets, and also to include data-driven AI weather models, and create diagnostics specific for that. And we will also improve the user interface to create the to feed the information to Silk, and also improvements into the web page. So, in summary, we have a new evaluation toolkit. It's still in development, but it has been very useful in some cases. It has been tested in anger during the past winter. Is designed around the concept of operations. Basically, we wanted something that was highly modular, highly configurable, and that we could pull in for a wide variety of users. And yeah, basically here you have the QR code, download that tray, and contribute. And Nareda, tēnā koutou, tēnā koutou, tēnā koutou katoa.
Awesome. Thanks a lot, Jorge. That was a great talk. So far, there's one question in the chat. If you've got any other questions for Jorge, please add them. And we'll start off with Alex. Pletzer asks, says that it sounds like CSET is similar to the NCO operators. Do you want to comment on that?
I'm not familiar with the NCO operators.
Alex, do you want to?
Oh,
NetCDF operators.
NetCDF operators. Is that a library?
Yeah, so these are just tools that you take an etcdf file and then you can apply some operations on them, and it's basically a set of executables, as I remember, and the kinds of operations you can apply are sort of averaging and interpolation and all these kinds of things.
Yeah.
It doesn't have graphics, and it's probably only supporting the CF conventions.
Yeah, and one of the things that we wanted to do is that these operators can be chained inside the CSET using the recipes. So you can, with very basic building blocks, you can build quite a complex diagnostic at the end. But you don't need to recode all the diagnostic. You just all the kernels are already coded there for you. So you just only need to stitch them together.
Yeah, the NCO I think allows you to do that, but maybe what NCO then would do is you have to create some intermediate files. So you create one file and then apply an operator to another. Whereas here you might do it in memory. Is that correct?
Everything is done in memory and is much more efficient. Yes.
Thank you, Jorge.
Cool. Next questions from Maxime. Does CSET provide scorecards for multi-model comparison?
That is one of the developments that is coming in. It will not be part of CSET. It will be part of MET and MET Plus that provide that capability, because at the end of the day, it's a statistically based comparison that those scorecards provide. And that is the MET Plus part of the CSET workflow.
Awesome. And Emily says she's interested in hearing more about the user role-playing approach in designing your tools. What would your advice be for ensuring we make tools and interfaces that actually satisfy end user needs?
Yeah, very interesting question. We knew, and probably that was perhaps a bit forced onto us, because we knew that we had to interact with users of many different backgrounds, with many different expertises, and that will interact with the tool in a different way. So we started designing those user stories like, Jorge knows how Iris works, has knowledge in Iris, and can do development of operators. And he has found that has an operator that, or a diagnostic needs a new operator, and he's happy to code that himself without the need of a maintainer. And we'll just interact with the maintainers when trying to incorporate or when doing the code review and the scientific review to get that that code. And it was just imagine that, so knowing what our use base was, trying to imagine that level of so.
Thanks. That's a great answer. And I am a supporter of design thinking like that for all research.
Yeah, I would say to ensure that we make tools is that that are suited for end users, is that we always consider end users. We need to know who is using the tool, so the tool is useful.
Perfect. Thanks a lot again, Jorge, for sharing your great talk. So that's all the time we have for questions for Jorge. If you've got any further questions for him, just stick them in chat, and Jorge, maybe you can monitor that. Next up, we have Bushra Anam from University of Canterbury, who's going to be speaking on scaling materials discovery with HPC and AI. Bushra, do you want to try and share your screen?
Hi everyone, good afternoon. Hi, can you listen me?
Yep, can hear and see you.
Yep. Hi, I would like to share my screen. Yep. So.
Perfect.
Can you see it?
Perfect. Yep, go ahead.
So, hi everyone. My name is Bushranam. I'm from University of Canterbury, working on materials, ferroelectric materials, energy efficient ferroelectric materials. And when I have started my PhD, I was like doing the computational modeling on advanced and new materials. But as we all know that how everything is changing with AI, this field is also revolutionizing every day. So it's like changing at such a great speed that it's very difficult to like chase it. I try to discuss that how we as a material scientists using theoretical powers can run into this like base. So today's my topic is advancing material informatics, data science and AI in unveiling new material properties. So what if we would like to design the perfect materials like semiconductors and insulators for quantum computing by simply analyzing the data? We all know that it's like it was very challenging for materials discovery, like vast chemical structure possibilities, too many tests experimentally, and our traditional approaches were limited by time, cost, and complexity. We needed like a faster and scalable methods, and where it comes, we can take and help from data. From in that branch is the material informatics. That is increasingly in an increasingly data-driven world. The material science and AI gives there is a new field of material informatics. At its core, this discipline utilizes advanced computational techniques, machine learning algorithms, statistical models to accelerate the process of material development and optimization. By using the data-driven tools, scientists can rapidly identify the properties, structures, and potential applications of large materials. So, so what we do is like material informatics, predict properties and new materials using the data. We use the data from experiments and simulations, the simulations like density functional theory, electron structures, compositions, and then materials database. We use AI and to extract the data, structured data extraction, pre-processing, data reduction, and then we use modeling and optimization using machine learning, relationship mapping, optimizing, and classification and clustering to identify, like based on the thousands of data we have for already existing materials, if the structure is changed, and by getting an input parameters we can predict that what will be the possible material will be and what are their properties would be. If we get the good results, then the next step would be we can take that material and test in our labs, and it can reduce our time for material discovery. Initially, we focused on computational methods to stimulate material properties, but the computational power and we are limited by the computational power and algorithm complexity. There is a significant growth in computational capability over recent years. AI now predicts material behavior and helps us in identifying new materials. Machine learning has become a catalyst in shaping the future of material science. AI-driven predictions enhance material discovery, optimization, and performance evaluation. Industries like healthcare to aerospace benefits from the faster innovation in material design and application. So, like here, applications of AI in materials research has improved due to the advancement in machine learning and deep learning protocols. Like here, you can see in this slide that it's just the representation of what I have already discussed. We have the simulation results. We put it into a data which is a structured one, and also from the experiments. Then we use the machine learning algorithms. We do the training and validation, and then we get the structure classification. We can get the new material designs, and then we can do the new property prediction. Material scientists use techniques such as classification, regression, dimensionality reduction, and cross validation, assessing the material structure property relationships, finding the sorry properties like formation enthalpies, predicting the desirable properties, and designing and developing novel materials. All these developments can be arranged in three steps, like having an acceptable sized data, then the protocol or computer program to learn from the data for meaningful conclusion, and then the augmented knowledge that provides by adding the advanced complexity, like by the deep learning, like neural networks. The machine learning frameworks are characterized into three distinct like areas: crystal structure prediction, and then selection of appropriate features, descriptions, and property predictions. So, coming towards the machine learning techniques, of course, we know most of these in the other field, but in respect to the material, like machine learning, in the materials informatic, machine learning algorithms include supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. And there so among them, unsupervised learning is mostly used for clustering and dimensionality reduction. Supervised learning is most commonly used for predicting and including linear regressions. And then most algorithms can perform both like regression and classification tasks, and supervised learning regression models are widely used in material science due to their like ease of interpretation. To have a complete material science study, it is sometimes necessary to compare multiple models, the principle of related algorithms. What is I can give you an example of one specific one, that is the convolution neural network. This is the CNN, are crucial for image-based material research, analyzing structure property relationship from images. Um, uh, Going deep into the neural networks, we have a convolution layer that extracts the local features from the images, then a pooling layer which reduce the image resolution and simplify the data, fully connected layers that combines the extracted features to make predictions. So CNNs are highly efficient at processing materials images such as atomic structures, helping researchers predict material properties like band gaps. Recent advancements in material imaging enables the acquisition of high quality data for functional materials. Uh, Using a novel microstructure representation, it is like successfully differentiate between micrographs relate and then we have microstructures that can hold the, like data on materials, processing conditions, physical and mechanical properties. And the recent advancement in imaging techniques like scanning transition, electron microscope, and atomic force microscope allows for high quality data acquisition that we can use in those machine learning models. Understanding the processes, microstructure, and properties relationships, that's what the fundamental goal is. So combining advanced image techniques with machine learning models, we can get a real-time analysis of the characterization data. So these approaches are successfully mapping microstructure images to the processing conditions, achieving this the success score of over 95% in complex material systems. Here's an example of microscopic image of the microstructure from a paper. We have the images that we can use in the to identify the materials. Uh, by these images, microscopic images, it's just a sample. We can, if we have a new structure, and then we can just put this into that, and we can get the like in our model, we can easily identify the new materials, like what those new materials are. So deep learning, there are like I'm discussing few of their applications. Like deep learning when applied to the alive microstructures, CNN is used to recognize different forms of alive microstructures that I have explained, identifying structures like spheres, polyhedrons, needles, Chinese script, twins, and dendrils. So there are different I could say techniques like dense net 201 that is used as a feature extraction, and it can achieve up to 21.2% accuracy. Efficient classification of complex patterns can easily be done. So these are just the advantages. Why there are of course some challenges. We can like avoid challenges in the physiologics typically encountering when distinguish between similar morphological forms can be applied, but these CNN models can be applied to any microscopic image data with minimal configuration. Uh, now, there are some challenges that we face with this evaluation of the approaches. Material sciences is evolved from uh, is evolved to the computational modeling. Earlier researchers lacked quantitative methods like thermodynamic and physical models. They are developed later with advancements in computers and simulations like density functional theory and molecular modeling. We can enable like complex real world modeling. So, but how we can achieve this even though existing databases and then when we discuss about like several databases are now available online that can serve as a source of the materials processing structure property performance relationships inorganic crystal structure data set database atomic flow material project open quantum materials database and novel materials discovery. Even though existing databases are like regularly updated, um, like challenges still exist on the appropriate features to capture the properties of materials from machine learning models, computational timing, cost, and power. So, when we when we move from there to like enhancing barriers to the implementation, like a transition to the practical applications, it's like materials. One of the main reason is the feature selection methods we use improving predictions is the improving predictions with the machine learning models. So one of the main reasons is there like in the recent years feature selection methods have made improving like model accuracy. By utilizing domain knowledge, this technique can improve with the more data we can improve the feature quality and enhance the predicting models. This can help us with the more efficient key material properties like melting point, hardness, and conductivity. The development of like high performance predicting models will be key in overcoming the limitations of computational and experimental methods, allowing for the more rapid and accurate predictions. So, future of material informatics, what will be the future? Future development in machine learning are expected to produce predictive models with accuracy. These advancements will allow us to better understand and forecast material properties, revolutionizing material designs. We will have improved data integration, creating comprehensive material databases through text mining from scientific literature will be a game changer. That's happening by now. By aggregating valuable data or on molecular properties and reaction conditions, we will significantly enhance our predicting capabilities. Next, improving machine learning techniques. Advances in deep learning will lead us to the more efficient and accurate representation of raw data. As we improve our understanding of how neural network processes information, we will see more reliable and adaptable models in material informatics. And the next and the main one is like integrating machine learning with density functional theory will improve our ability to predict complex molecular features and study quantum systems. This will help solve like problems in computing chemistry and material science. These emerging trends will drive the future of material informatics and the convergence of advanced machine learning techniques with traditional computational methods will shape the next generation of material science like breakthroughs. So, data science and AI has become central to advancing material research, driving innovation and deepening our understanding of material properties. Machine learning, including techniques like unsupervised, supervised reinforcement learning, and deep learning, has revolutionized material science. It enables quick analysis of complex properties, predicts novel materials, and optimizes fabrication processes. Incorporating so uh, and also predicting modeling and structure properties, property correlation, and enhancing material synthesis and discovery. Machine learning facilitates precise prediction and custom material design, and combine the image processing. It can improve the object detection and classification. While machine learning presents potential challenges related to data quality, algorithm complexity, and ethical consideration must be addressed. So, ongoing research and collaboration are very important for overcoming these hurdles, and like we can use the machine learning in material science. Yep, thank you. That's what I just tried to highlight what's going on in material science using the AI and data science analysis.
Cool.
Yep, thank you.
Thanks a lot, Bushra, for that that great talk. Unfortunately, we have no time for questions for Bushra, but if you have any questions, maybe just add them to the chat, and Bushra, you can address them in writing. So that brings us to the end of our day. Thank you everyone for joining this session and the 2 days in general. And I've really enjoyed it, so I hope you have too. I'm going to pass it over to Mercedes, who will give some closing remarks. But thank you all for your company.
Thank you, Janet. So again, that brings us to the close of the second day of NZRSE 2025. We really, truly appreciate the time, effort, and commitment each of you has made to be here over the past 2 days. So thank you for your contributions. It really has been some interesting talks that have been brought forward and some great conversation. It's fantastic that as a community we can hold events like this to share what we're working on, exchange ideas, and engage in conversations that we might not have had otherwise, especially given this diverse range of expertise and presentations on offer. I'd like to quickly reflect on the conference as well, because we've had such great speakers sharing their knowledge and insights, and this was actually a really great outcome of attendees joining us throughout this event, with an average of 60 attendees who are active throughout each session. So we're incredibly grateful for your presence, and we understand it is not entirely feasible for everyone to attend the extent of both days. So thank you for everyone for coming along. The level of engagement has been really great. We've seen some interaction, lots of interaction with thought-provoking questions and discussions that added significant value to the sessions. Your contributions have enriched the conversations and helped broaden perspectives across a range of topics. So thank you to everyone for that contribution. Also, I'd like to extend a special thank you to the organising committee for their tireless efforts in bringing this year's conference to life. Your hard work behind the scenes ensured that everything ran smoothly, especially chairing all of the sessions, and we owe the success of this event to your dedication, so thank you. I'd also like to thank the RSE AU NZ Steering Committee for their continued support in making this event possible. Of course, none of this would be complete without our wonderful presenters and attendees. And lastly, I'd like to have a special thanks to our keynotes, Nick and Emily, whose inspiring talks set the tone for these incredible 2 days. Looking ahead, I'd just like to point out that recordings of the session will be added to the Rianne's YouTube channel at some point in the next 2 weeks. So we'll send out an email to let you know when that is available for viewing. If you have not given us permission to share your presentation, that's fine. Those will be edited out, but we'll let you know so that you can share those on as well. We'll be sending out post-conference surveys, and we really do want to hear from you. What did you enjoy? What could have been improved? And how can we make next year's conference even better? Your feedback really is invaluable and help us to shape future events, and actually what has got us on Zoom this time. So we'll see how that goes for next year. So once again, thank you to everyone for being here. It's been a privilege to share this space with such passionate and knowledgeable individuals. And if you would like to reach out, you can just use my email address that is listed on this page, because I'll be contacting you as well in the next few days. You'll have somebody to reply to. You can also go onto the NZRSE or Rianne's website and go through the support, and that will get through to us as well. So again, thank you for your input over the last 2 days, and we do hope to see you again next year. Thank you, everyone, and we'll see you next time.